Hello students, this is your friend Sumit and today we are going to discuss topic 6 of our JEE Mains Crash Course series, that is current and electricity. Current and electricity is one of the most important, at the same time the topic which is having one of the highest weightage in JEE Mains. In JEE Mains we have seen there are 3 questions in some of the shifts from this particular chapter. These 3 questions were just straightforward, very easy questions. If you understand the concept, quickly you can solve those questions, and some of the questions like may take some time but hardly like 1 minute. Okay, so the point is, don't miss anything of this video. I'm going to discuss all those key concepts in a detailed form. I'll show you the varieties of the questions, I'll solve those questions, I will tell you how you can save time in those questions. So make sure you watch this video fully, and at the end must comment that you watched it fully. Okay, also don't worry about the notes, because after the class you'll have the notes as well as the practice sheets, because practice is most important thing. So notes and practice sheet where you'll get on the PW app. As you know, many of the students by taking help of PW app are having great AIR. So the link is there in the description box. Click on the link there. From there you'll go to the PW app, join the free batch there, and there you'll have the notes and the sheet of this class. Okay, so let us begin the discussion. So we'll be covering entire thing, all the subtopics and topics from current and electricities. Few of them I have mentioned, but if I didn't mention few topics, we'll be covering everything that is important for JEE Mains. Okay, so first of all, electric current. What basically current is, let us take a conductor is there. Okay, so if I take any cross section, so how much amount of total charge per unit time that is crossing that cross section, I will say that is equal to my current. So if I say, let us take in interval delta t, my charge that is crossing here is delta q. So I will say the current will be delta q, the charge per unit time. Okay, now this delta q by delta t, what I will say this as the average current. Okay, I'll say this is my average current. And if I want to find the instantaneous current, so I'll just differentiate. Instead of this delta, I'll use d. So that is dq by dt. Okay, so this becomes my instantaneous current. Now sometimes what happens in a question is given like this much amount of charge passes through in, let us take 1 minute or 2 minutes, then find the average current. So that there you have to take delta q divided by delta t. And if it is saying that the, let us take some expression is given as a function of time, and then he asks you find the current at this particular time. Expression for charge is given. Okay, so there what you need to do, dq by dt, simple. Okay, now generally if I talk about a conductor is there, the electrons in absence of electric field would be moving randomly. So in absence of field, if you ask me whether the electrons are moving or not moving, I'll say electrons are moving. Even if the battery is not connected, the electrons in a conductor are moving, but they are moving randomly. So on an average, if I talk about in absence of electric field, how many electrons are passing through a cross section? Okay, so the same number of electrons will be passing both the sides. Okay, therefore we say in absence of battery or electric field, the current will be zero. What happens when let us take battery is connected, then electric field is applied, okay, here in this direction. So what happens, electrons still would be moving randomly. Okay, it's not that electrons would all be moving in one particular direction only like this. No, electrons would be moving randomly, colliding like that will happen. But on an average, if I talk about, the charge will be moving. Okay, let us take here electric field is this in this direction. So the we will consider that the positive charge is effectively moving in this direction. The direction of current, you know, that is the direction of the positive charge, but we know electrons are moving, they are negative. So electrons move in the opposite direction. Okay, we'll come to those details back. Now let us discuss a question. The electric current through a wire varies with time as this, where I naught is given as 20 ampere and beta is 3 ampere per second. The amount of electric charge crossed through a section of wire in 20 seconds. Now current is given, I want to find charge. So I know that I is equal to dq by dt. Okay, So from here I can say that dq is equals to I dt. I have to find the total charge in an interval of 20 seconds. So my time will go from 0 to 20. Charge will go from 0 to, this is 20, charge will go from 0 to q. Let us take capital Q. From here I got q is equals to integration of what? Integration of current. This is I naught plus beta t. So I'll write this as I naught plus beta t dt integration from 0 to 20. Now if you integrate it, what it will become? I naught integration will become I naught into t. I naught is a constant, okay? So this will become I naught into t plus beta into t. Now beta is a constant, we'll take that out, t integration t square by 2. So you know the rules, huh? So this is beta t square by 2. And here I'll put my limits from 0 to 20. Now here I have to put the values as well. So I naught is 20. So this is 20 into 20 plus, what is this? Beta is 3. So 3 by 2 into, this is again 20 square. 20 square. So 20 square I can take out as common. So this is 400 into 1 plus 3 by 2. Inside it will become 1 plus 3 by 2. So that is 5 by 2. So 2 into 200, and this is 1000. Now if I ask you what is the unit, that is coulomb, unit of charge. What is the unit of current, by the way? What is the unit of current? If I talk about unit, that is ampere. Okay, that is the SI unit. But ampere is actually a bigger, you can say, quantity. Like 1 ampere current is quite high, I'll say. Okay, normally if you talk about the ratings of the wire that we have in our homes, so that is 0 to 5 ampere. Okay, so you can understand, like 1 ampere is a big value. Okay, so generally if you talk about 100 ampere, or like, they are very, very big values. Okay, generally for small appliances that we have, let us take we are having a cell. Okay, a small bulb is connected with the cell. How much current is there in the wire? Okay, there, that current will be in milliampere. Okay, like that. Now this is, I'll say, the most confusing topic for the students: the relaxation time, the drift velocity, the derivation for the resistivity, and a conductivity relation, the electric field relation. All those things are very, very confusing for the students, but I'm going to explain you these things in a very simplified manner. Okay, so you'll get all these things provided you are attending this video with attention. Relaxation time. So I was saying that a conductor is there. So the electrons are moving. Let us take electron move like this. Okay, it will collide. Collide with what? It can collide with another electron, or it can collide with the you can say the ions that are there. Okay, so it will collide with the positive ions. Collide. Let us take it, collide, then it will move like this, then it will move further like this, then it will move, then it will move like this, then in this direction, then in this direction, then in this direction, like this. It will be moving somewhat. Okay, here I am saying that electric field is in this direction. Electric field is in this direction. So on an average, if I talk about, the electron is moving towards the right. It is, on an average, it is moving towards the right. Okay, colliding, it is coming back, then again colliding like this, moving randomly, but on an average, if you talk about, it is moving towards right when electric field is there. If electric field was 0, if E is 0, then on an average you will say that is 0, moving like this, in this direction, then colliding, then, okay, so it would be moving randomly. But here I'll say, on an average, if I talk about the velocity, that is 0, on an average. Here V average is not 0. So electron is moving, colliding, then moving, then colliding. So this duration between two collisions, the average duration between the two collisions, we call that as the relaxation time, and we denote with tau. So this is my relaxation time. And what it is average duration between two collisions. Electric field is there. Let us take some initial velocity of the electron was u. Okay, some initial velocity was u, and the electric field is providing some acceleration. How much acceleration will be there? So I'll say that acceleration is equals to force divided by mass. How much is the force? Force is electric field into charge. Electric field I am denoting with E vector. Charge is minus E. So into charge, this is the force divided by the mass of the electron. So this becomes my acceleration. Okay. This becomes my acceleration. Now here negative sign represents that the direction of acceleration is opposite to the electric field, because we know that the charge of the electron is negative. That point is clear to us. Now if I ask you, it is colliding, okay, and then it is being accelerated and then again colliding. So what will be the velocity just before a collision? If I say, so I am using V is equals to U plus AT formula. Acceleration is constant, I can use this, yes. So I can say V is equals to U and acceleration is minus EE by M into T. Now let us take average both sides. Average I am taking for all the electrons. So all the electrons, if I talk about this V, we will say that is my drift velocity. Okay, that is my drift velocity on an average with how much velocity the electrons are moving in a particular direction. That is my drift velocity. So I will say this average of this so here this becomes my V drift. Average of U, that is 0. In absence of electric field, the average velocity was 0 minus EE by M into tau. Tau is the relaxation time. So from here I got the expression for the drift velocity. Negative sign is there, but if I talk about the magnitude of the drift velocity, okay, I'm just talking about the magnitude. So what I'll say magnitude is equals to E into electric field divided by M into tau. That is my relaxation time. We got this. This will say effectively, if I talk about with what velocity a particular electron is moving, I'll say that is V drift. If you see what actually the speed is inside the conductor of an electron, that is near to the speed of light. Okay, near to the speed of light, a bit less than that, but that is very, very high. Okay, because that speed is very high, but randomly it is moving. Therefore, effectively, when you find that my drift velocity, that comes out to be very, very less. Drift velocity, if you talk about, that is in mm per second. Okay, and actual speed, that is in, you can say this is 10 to the power 8 meter per second is of that order. Okay, now let us relate drift velocity and current. Sometimes students are confused, like the drift velocity is very less. So how is that possible? Like when we press a switch, immediately the bulb is on. It should take time because the electron will go and then it will travel till the bulb and then the bulb will, lit. But it's not like that. It's a continuous flow. Although the speed is very less, but it's a continuous flow. So therefore, immediately when you switch it on, okay, immediately the bulb or the tube, or I'll say fan, that is switched on. Considering this as conductor, I'm taking a cross section of this cross section. Electrons are moving with what speed or with what velocity, average velocity, that is my drift velocity. So electrons are moving with drift velocity like this. I want to relate drift velocity and current. So basically I know that current is basically in an interval delta t, if charge that passes is delta q, so that is my delta q by delta t. So what is delta q? How many number of electrons that passed into the charge of the electron. Charge of electrons into the number of electrons. Number of electrons will be, I'll say here I'll define n, that is number of electrons per unit volume. Okay, this is number density of the electrons, or you can say, so this is basically number of electrons per unit volume. Okay, so it is moving with velocity, let us take Vd. Okay, so how much volume that will pass, that is Vd into delta t. Vd into delta t is my length and into the cross section area A. So volume will become area into Vd into delta t. And these many, this is the volume into the number density into n. So these many electrons are passing divided by my delta t. It is passing in delta t time. So delta t got cancelled and I got a relation that I is equals to NEA into V drift. This formula is important. You should remember this formula, which relates the current and the drift velocity. Now from here, one more thing, I can define the current density. Okay, current density is basically, you can say, that is current per unit area. So here if I write I by A, this is NE into Vd. Okay, and from here I can say my J is NE into Vd. Current density is basically a vector. Current density is a vector, and generally if I talk about, like here uniform conductor is there. Okay, so my current density is in this direction. So J dot A, when I say that is my current, I'll say here my current, that is J dot area vector. Area vector is towards the right, angle between them is 0. That is JA cos theta, and in this particular case JA cos of 0 here, that is my J into A. Okay, here. But if the condition is like that, here there is some angle between the area vector and then J. So then you need to consider that particular theta also. Okay, so that relation will come accordingly from here. Now I related my current and drift velocity. Now what I can do is, let us write drift velocity in terms of electric field and the relaxation time. So if I write I, that is equals to NEA, V drift is E into electric field. I'm not putting the directions, okay. So EE by M into tau. And from here J becomes equal to NE square into E electric field into tau by M. And I can say, I can rearrange this by taking E out, and this becomes my NE square tau by M. NE square tau by M. And this thing becomes my conductivity. That is sigma, and this conductivity is opposite of resistivity. Okay, you should understand the relation. Sigma is basically 1 by rho. Rho we say resistivity of the, we will come to resistivity also. Okay, rho is basically the resistivity. So I can write this formula as sigma into E. And other way, if you see, we know the Ohm's law, V is equals to IR okay, and R is equals to rho L by A. Potential difference divided by length, if I take, what that will become, E, electric field, is equals to I by A becomes my J, and rho is my resistivity, and resistivity is 1 by conductivity, so J is my sigma E. Okay, so basically this expression is sigma only. Therefore, I am saying that expression is my sigma, that is conductivity. Getting it? Okay. We'll come to Ohm's law also, and the resistance, resistivity relation, all these things, resistance and resistivity, we'll talk about that in a while. So from here, what you need to remember, this is important, this relation, J is equals to sigma E, and what else? This relation. Okay, so these fundamental relations, you need to learn them so that you can apply them, because questions are asked not very frequently from here, but questions are asked from this in mains. Let us come to questions. Drift speed of electrons when 1.5 ampere of current flows in a copper wire of cross section 5 mm square is V. Now V drift is given to us. Here you see this is the drift speed of electron when 1.5 ampere of current flows in a copper wire of cross section, this is the cross section and this is my drift V. If the electron density in copper is this, so what is this? This is my N, small n, electron density that I considered. The value of V in mm per second is close to, okay, so current is given, area of cross section is given, N is given, I need to find V drift. So I know I is equals to N E A into V drift. This relation we know. So from here I can say V drift is I by N E A. What is I? I is 1.5. What is N? N is 9 into 10 to the power 28. E 1.6 into 10 to the power minus 19 into A. A is cross section is 5 mm square. I need to convert that to SI units. So this will become 5 into 10 to the power basically minus 6. Yeah, minus 6. So this is minus 25. So this will become 10 to the power minus 3. So mm thing I got. So this is 1.5 divided by 1.6 here, 5 here and 9 here. What it will become, this is 0.3. 5 into 3, okay, and 3 into 3, so this is 30 here. So 1 by 48. Am I right? Yes, 1 by 48 into 10 to the power minus 3. So nearly I can say this is 1 by 50 mm per second. So what is 1 by 5? That is 0.2, 0.02. 1 by 5 is 0.2 and 1 by 50 0.02. So that is 0.02, nearly 0.02. Perfect. Just need to put the values. Okay, here you'll see the varieties are very less. Okay, the formula like I is equals to NA VD is there, J is equals to sigma is there, I is equals to J by A is there, so J is equals to I by A is there. So here there are very less varieties, and drift velocity from electric field relation and relaxation time we know that is E into E by M into tau. So these 3-4 formulas are there, just memorize them nicely. Okay, any question is coming, you can tackle that very easily. Let us see this also. A cylindrical wire of radius 0.5 mm and conductivity 5 into 10 to the power 7 is subjected to electric field of 10 millivolt per meter. The expected value of current in the wire will be this, the value of excess. Okay, here electric field we know, conductivity we know. From there I can find current density, and using current density I can write my area. I can write my current, okay, into area, multiply by area, that will become my current. So J is equals to sigma E. Let us find J first. Not let us find J, I am just writing it directly. So I is basically J into A, okay. So what is I? Sigma E into A. Now let us put the values. What is sigma? Sigma is 5 into 10 to the power 7 into electric field is 10 millivolt per meter. So 10 to the power minus 3 into area. Area is pi r square. So into pi. Radius is 5 into 10 to the power minus 4. Square of that will become 25 into 10 to the power minus 8. Is that fine? Okay. Now, this is minus 3 and this is 8. So, this 8 and 7 minus 1. So, minus 4 will remain here. Minus 4. Yeah, 10 to the power minus 4 is there. So, 10 is also there. So, 10 to the power minus 3. So, this will become in milli. Let me say this is milliampere, and this is 5 into 25 into pi. So what is that? 5 into 25 is 125, that is basically 5 cube. So this is 5 cube into pi milliampere. And what is x from there? X becomes 5. These are simple questions, not that much complicated. Although the derivations, if you see, relaxation time, the drift velocity, they seems a bit complicated. But if you understand that very clearly, things are very easy here, straightforward. Now Ohm's law, we know that V is equals to IR. Now V is equals to IR is generally we say that is for conductors. We consider that the resistance is constant, here the slope is constant, and if we try to plot it from here, so it goes like this, and the slope of this theta, so I'll say R is basically tan theta, V by I, and this is for ohmic devices. For ohmic. Now few of the, I'll say, conductors or materials will not follow ohmic law, okay. That relation will not be straight line. Let us take, if you talk about semiconductors, that relation is not a straight line. The slope is not constant. The slope there, what we find is basically we find dynamic resistance. There we find the instantaneous resistance there, the instantaneous slope there, because the resistance is not constant in that particular case. That is not a straight line in that particular case, okay. Now resistance and resistivity, if I talk about resistance, then you will say that resistance is basically V by I. But the point is, resistance is independent of V and independent of I. R is not dependent on V and I. That is equal to the ratio of V and I. If V will change, I will change, but R will remain the constant, okay. So basically what, on which things R depends? R depends upon the dimensions and the material property. So R is rho L by A. Here, if a conductor is there whose length is L, area of cross section is A, and the resistivity of this is rho. What is resistivity basically? Resistivity is the property of the medium. It tells you how much you'll say the favorable or unfavorable the medium is for the flow of the electrons. Greater the resistivity, more resistance to the flow of the electrons. Lesser the resistivity, more favorable it is for the flow of the electrons through it, basically, in simple words if I say. Now here if you see, this L here is my length, of conductor, A is area of cross section, rho is the resistivity. Resistivity is property of the material. Resistivity is independent of the shape and size of the material. If I talk about the resistivity of an iron rod, which is having, let us take a radius of 5 mm, and an iron bar which is having a greater cross section area, okay, resistivity will be the same because the material is same. Resistivity is independent of the shape and size of the material. It depends on the material property it is. Yes, if you change the temperature of the material, the resistivity will change. Okay, if you change the temperature, the resistivity will be changing. But if you change the shape, it will not change. Resistance will depend on the shape. If you change the shape, the resistance will change. Okay. Now here I am talking about a cylindrical bar having a cross section area A, length L. There I am saying that resistance is rho L by A. What if there is some non-uniform shape, the cross section area is changing, or some you can say some things are like that. So what you need to do, there we need to integrate. We will take small sections, okay, each resistance we will find, and then we try to find the total resistance. That we do. Now let us do some questions on this. Two wires A and B are made up of same material and have the same mass. Material is same means the resistivity is same. Wire A is having resistance of 2 mm, wire B is having radius of 4 mm. The resistance of B is given to us. What is the resistance of A? Few things you need to understand from here, that both have same resistivity. Resistivity is same as the material is same. Next thing, material is same, density is same. Density is same, here it is saying that mass is same. If density is same means the mass is same and density is same means the volume is same. So volume of both the wires A and B, I don't know, whatever their shape and size may be, I am considering this as A, this as B. Both are having same volume. So I will say volume of A, this is equals to volume of B. Now the radius of A has a radius of 2 mm. So here I will say volume as area of cross section into the length. Okay, so this is area of cross section of B into the length of B. What is radius? That is 2 mm. What is radius of B? That is 4 mm. So area of B will be how much times? 4 times of area of A. Area of B will be 4 times of area of A. Therefore, I can say that length of B will be 1/4 the length of A. Getting it? 1/4 the length of A. Now write the resistance. If I say resistance of A, that is rho into LA by rho L by A, area of A. Now if I say resistance of B, that is rho length of B. Length of B is 1/4 of length of A. So 1/4 length of A divided by area of A. So area of divided by area of B. Area of B is 4 times the area of A. So 4 times of area of A. So what it is now? This is 4 into 4, 16. So this is basically 1/16 into rho L by A, that is the resistance of A. Now resistance of B is given as 2 ohm. So if I put 2, so RA will become 32. This is what we need to mention. So this is 32. Now in question he will not say the resistivity is same. In question he will not say the length relation and other things. He is indirectly saying those things, that volume is same. How volume is same? Mass is same. Material is same, so density is same. We need to understand that. From there we got volume is same. From there we related lengths. Area of cross section relation is already given, and there we got the relation of the resistance. Getting it? Easy questions. You can do them very quickly actually. When I'm saying here, I'm explaining the things to you. So here I'm taking time, step by step. Now this you have to write. Now this you have to write. But if you do this question in exam, hardly it will take 20 seconds to solve. Now temperature dependence of resistivity and resistance. When temperature rises, what happens? Let us take conductor is there, you are increasing the temperature. So oscillations will increase of the positive ions, okay, the oscillations will increase. So what will happen? There will be more collisions with electrons. More collisions means greater resistance. Greater resistance means the resistivity is greater, okay. So when you are increasing the temperature, basically the resistivity is increasing. Resistivity will increase. Now one more way you can understand this is from previously when we mentioned the formula for resistivity, conductivity, that thing, from there also you can see. From here if you see, this is my conductivity. Tau is relaxation time. Increase the temperature, collisions will increase, frequency of collisions will increase, so time will decrease. Time decreases means conductivity decreases. Conductivity decreases means resistivity increases. Getting it? That way also I can say this same thing. So with the temperature, the resistivity is increasing. So if for conductors I talk about how it varies with temperature. So it varies like this. The variation is, the slope is not that great here. Let me take a straight line. Yeah, somewhat like this. This is how it varies. So it is here this is my temperature, okay, and let us take this is rho naught at T is equals to 0. This I am taking in degrees Celsius. Let's take, okay, this is my 0 degree Celsius here. So 0 we are taking as a reference. So resistivity, any particular temperature rho, if I talk about, that is my rho naught into 1 plus alpha delta T. Rho naught at 0 degree it is rho naught, okay, when delta T is 0, okay, as delta T is increasing, rho will keep on increasing. This is alpha, and what is that? This is thermal, you can say coefficient of thermal temperature coefficient of resistivity, okay. Temperature coefficient of resistivity. What is its units? Units you can say 1 plus 1 is you can say this is rho by rho naught, that is dimensionless, so 1 is dimensionless, alpha delta T is dimensionless, so this is per degree Celsius, that is the unit. And from here if you want to relate the resistance as well, so let us multiply L by A both sides. So what it will become? Rho L by A here, that becomes my resistance. This will become rho naught into L by A, that is my R naught resistance, okay, at reference temperature into 1 plus alpha delta T. We take reference as 0 degree Celsius. Many places you may see this mistake, and that mistake is they sometimes consider the reference, like the resistance was given at 15 degrees Celsius, they are asking resistance at 20 degrees Celsius, okay. They'll consider 15 to be reference, and from there they'll write that the resistance at 15 into 1 plus alpha delta T becomes my 5. So there comes a mistake, and sometimes when you solve the question like that, there might be like some greater variations in the answer also. It can happen. So basically my reference is 0 degree Celsius, you need to understand that. A reference is at 0 degree Celsius. At any other temperature if I am talking about, To find the resistance, I'll say R is equals to my reference resistance at 0 degrees Celsius into 1 plus alpha delta T. Alpha will be given to you in the question. Similarly, if I have to find resistivity, I'll use this formula to find the resistivity at any particular temperature. One more thing, this relation is for conductors. Okay, if let us take you talk about semiconductors, with temperature what happens? The resistivity decreases, because as the temperature increases, so there you can say more number of electrons are available for the conduction. So there actually there what happens, there more number of electrons are able to go to the conduction band. So more numbers of electrons are able to take part in conduction. More number of electrons are conducting now. It means lesser will be the resistivity now. But here the resistivity is increasing in case of conductors. Let us solve this question. Resistance of wire is measured as 2 ohm and 3 ohm at 10 degrees Celsius and 30 degrees Celsius. The temperature coefficient of resistance of material of wire is. Now, taking reference at 0 degrees Celsius, I am taking that R naught is the reference resistance. This is resistance at 0 degrees Celsius. Now, for both the cases, 10 degrees Celsius and 30 degrees Celsius you write. Now, at 10 degrees Celsius, the resistance is 2. We know the formula R, that is R naught into 1 plus alpha delta T. So, what is R? R is 2. So, 2 is equals to R naught into 1 plus alpha, and what is delta T? Delta T, 0 is reference, so 0, 10 minus 0 is 10. So, this is 10 alpha. Another case, when it becomes 3 ohm, okay, 3 ohm will become at 30 degrees Celsius. So, 3 is equals to R naught into 1 plus into alpha into delta T. Delta T is in case 30, 0 minus 30 minus 0, that is 30. These two equations you got, we'll divide them. When you divide them, R naught will cancel out, and from here if I write it, it will become 2 plus 60 alpha, and this is equals to 3 plus 30 alpha. And what it is now from here, 30 alpha comes out to be 1. So alpha is basically 1 by 30. 1 by 3 is 0.33, so this will become 0.033 per degree Celsius. Can alpha be negative? Yes, alpha can be negative. Alpha can be negative for semiconductors. There the temperature increases, the resistivity decreases. So there the alpha will be negative. Here we are having a positive alpha. Two conductors have the same resistance at 0 degrees Celsius, but their temperature coefficients of resistance are alpha 1 and alpha 2. The respective temperature coefficient for their series and parallel combination is. In mains, many questions are asked from this particular topic. Okay, thermal coefficients. For resistivity, resistance relations to resistance, here they are connected in series, parallel, effective alpha they are asking. These type of questions are frequently asked, and we can expect this question also in, we can say, 2026. So make sure you understand this concept very nicely. Now here, two resistance, they are equal, but their thermal coefficient is different, alpha 1 and alpha 2. Okay, now they are connected in series one time and then they are connected in parallel. So what alpha effective is? Let us take first case 1, series. This is R1, R2. Now I know that two resistance are in series, so I know the series equivalent, that is R1 plus R2. I'm considering that this fundamental thing you already know. Now I'm increasing the temperature. Let us take, this was the initial at 0 degrees Celsius. Now I'm increasing the temperature by delta T. So what RS will become? RS into 1 plus alpha delta T. That way I can write, or what I can do is I can differentiate this equation also to find the direct relation between delta RS, delta R1, delta R2. Differentiate this. So differentiate this, it will become dRs is equals to dR1 plus dR2. That way also I can write. Now dRs what DRS will be if I increase the temperature by delta T? We know that R dash will become RS into 1 plus alpha delta T. So basically DRS is how much it increased, that is RS alpha delta T. Okay, so if I say DRS, so I can say that is RS into alpha dt. Okay, so DRS is RS into alpha into dt. This is R1 into alpha 1 into dt. This is R2 into alpha 2 into dt. dt same everywhere. This alpha is my effective alpha for the, because combination resistance is R series. Okay, so alpha here is my alpha effective. So alpha, if I say from, that is R1 alpha 1 plus R2 alpha 2 divided by R series. R1 and R2, they are equal, that is mentioned, and R series will be twice of that. So what it will become? It will become R alpha 1 plus R alpha 2 divided by 2R. So that will become alpha 1 plus alpha 2 divided by 2. That is coming in series combination. Now if I talk about parallel, case 2. Okay, let us write with different color. Now in parallel we are having two resistance R1, R2 in parallel. So from there I know that 1 by R parallel is equals to 1 by R1 plus 1 by R2. This relation I know. I need relation between the dr1, dr2, dr3. Differentiate it. So this will become minus 1 by R parallel square into dr parallel plus is equals to minus dr1 by R1 square minus dr2 by R2 square. You know 1 by x differentiation is minus 1 by x square. Therefore, I am writing it like this. Minus sign will get cancelled. Now dr1 by r1, dr1, drs by rs, what it will be? That is alpha delta t. So similarly, dr parallel by r parallel will be alpha effective into delta t. So it will become minus minus I am cancelling out. So this will become 1 by r parallel into alpha effective into dt. Similarly, alpha 1 dt by r1 plus alpha 2 dt by r2. Okay. Now R parallel is R by 2, R1 is R, R2 is R. Put it like this, dt will get cancelled. From here also you are getting alpha is equals to alpha 1 plus alpha 2 by 2. This relation is coming from here also, for whether it is series, you can say combination or parallel combination, the alpha effective is coming out to be alpha 1 plus alpha 2 by 2. B option. These type of questions are frequently asked in mains. Make sure you have a good practice of that. Now mobility. Electron mobility is basically defined as the drift velocity per unit applied electric field. So if let us take electric field is E, so mobility we denote with mu. This is the drift velocity V drift divided by the applied electric field E. What is V drift? If I relate with electric field, so we know the formula, that is E into tau, the relaxation time, divided by M by E. Here E is getting cancelled and this is E into tau by M. M is mass of electron, E is charge of electron, tau is our relaxation time. This becomes my electron mobility. Question on this. Current is given 5 ampere, passes through a copper conductor, resistivity is given to us, the radius of cross section is this, the mobility of the charge if the drift velocity is this. Okay, so I'll say that mu mobility is basically V drift divided by electric field. V drift is given to me, I need electric field. For electric field the current is given to me the area of cross section I can find, the resistivity is given. So I know J is equals to sigma E. J is equals to sigma E. Okay, so from there I can say E is equals to, this is sigma is 1 by rho, so this is rho into J, and J is I into A, like that. Now put the value. Put it here basically first. So this is rho into I into A. Now here you need to put the values that are given to us. These questions are straightforward, just formula based, no variations. Like there is nothing, different you can ask from here. What you can ask from here? Only that these relation you can ask. Same relations we are using again and again. So what is VD? V drift is 1.2 into 10 to the power minus 3. 1.2 into 10 to the power minus 3 divided by rho is 1.7 into 10 to the power minus 8. So 1.7 into 10 to the power minus 8 into I, what is I? 5 into area of cross section. Area of cross section is pi r square and r is given as 5 mm. So pi into 5 square is 25 into 10 to the power minus 6, because that was in mm. Now from here we need to simplify, and if we see, this is 1.7 into 10 to the power minus 8, okay, that is correct. And this was I into A. I was 5, yes, that is also proper. 10 to the power minus 6. Oh, very small answer is coming, by the way. Is there any mistake we did? Let us check the values again. V drift was V drift by E. V drift E I wrote as J into rho, and J I wrote as I into A. Yes, now putting the values, V drift was 1.2 into 10 to the power minus 3, that is right. Rho was 1.7 into 10 to the power minus 8. Yes, and then I as the current, that is 5 ampere, into the area of the cross section, that is pi into r square. That was in mm, so this will become minus 6. Everything is fine from until here. Now everything is fine. Okay, now from here if I see what it will become, this is 10 to the power minus 8, so 10 to the power minus 14, okay, 8 and 6 minus 14, it will go in the numerator, so this will become 10 to the power, this is 14 minus 3 is 11, and this is 1.2 divided by 1.7 into 5 into 25, that is 125 into pi. Oh, I did a mistake actually. Got it. Where is the mistake? Here is the mistake. J. J is not I into A. J is I by A. Yeah, sometimes these type of mistakes can be there. Therefore, I was thinking it is coming too big. Yeah, coming a bit, you can say, back from here. You need to put the values again. Silly mistake. J, and J is I by A. Yeah. Now I'll put it. So E, that is rho I by A. Yeah. Now I think everything will be fine. I was thinking that this is coming too big. V drift is 1.2 into 10 to the power minus 3 into area pi into r square. Yeah. This. And rho is 1.7 into 10 to the power minus 8. And I is 5. Now this will be simplified. So this is 5, okay, minus 6 and minus 3, so that will become minus 9. Minus 8 we are having in the denominator, so it will become minus 1. So minus 1 I can write as 1 by 10. I'll take 10 here. 5 into 2. 5 into 2 it will become. Now in the numerator we are having 1.2 into pi. 1.2 into pi divided by in the denominator we are having 1.7 into 2. 1.7 into 2. And if we simplify from here, the answer will be nearly equal to 1. That is option B. Okay, we did a silly mistake before. Now everything is fine. Moving ahead. Combination of resistance. Now we are actually starting the chapter. Till here, there was some, you can say, deep things, the fundamental things, how the resistivity comes into picture basically, how the electrons moves inside a conductor, okay, that was microscopic things, the relaxation time and all those things. Now we are coming to the actual part of this chapter, the series combination of the resistance. We know the formula, R1, R2, R3 are in series, equivalent will be R1 plus R2 plus R3. Let us see how it comes. Now here total potential is V, okay. So when in this total drop is there across these three resistors. So across this I am saying the drop to be V1, across this the drop to be V2, across this the drop to be V3. So when I say total V, that will be V1 plus V2 plus V3. V is equals to IR. So V, total V is equals to my current here, let us take that as I, into R equivalent resistance. V1, here this current I will be passing through R1, same current will be passing through R2, same current will be passing through R3. So when the resistance are in series combination, the current through the resistors is same. This is how we detect whether the resistors are connected in series or in parallel, okay. So when we say here, the same current is passing through the resistors, same current is passing through the resistor, therefore we say these three are in series combination. Potential will not be same, they can be same, they cannot be same, okay. So it's not that V1, V2, V3 has to be same. If three resistance are equal, they will come out to be same, but the point is here the current is same in series combination, not the potential across them. V1 is I into R1, V2 is I into R2, V3 is I into R3. If I take I common, that will cancel out. So R equivalent comes out to be R1 plus R2 plus R3. If there are more resistance, R3 plus R4 plus R5, like that. Now parallel combination, we have connected these three resistors in parallel combination, potential is V. Now what will happen? Will the current be same in the three resistors? No. This current I is coming, that current is divided, okay. But if you see the potential across R1 is V, potential across R2 is V, potential across R3 is V. The potential across these resistors is same. So when we say the resistors are in parallel, the potential across them is same. And also you can see their ends are connected, like if two ends of two resistors are connected, okay, like that, so we will say the two resistors are in parallel, okay. That is a basic understanding, because when the circuits will come, when like many resistors will be there you need to identify which one are in series, which one are in parallel, to find the equivalent resistance, to find the current in the circuit, all those things that will come, we will come to that practice also, okay. So here if I say this current I is coming, this is divided into three currents, I1, I2 and I3. So I will say my I current is I1 plus I2 plus I3. What is I1? Potential is same. So V by R1, I2, V by R2, I3, V by R3, I, V by R equivalent. So here I am getting 1 by R equivalent to be 1 by R1 plus 1 by R2 plus 1 by R3. That is the parallel combination equivalent resistance. If there is 4 resistance, you can write 1 by R4 plus 1 by R5, like that. 2 resistors are there, 1 by R equivalent is equal to 1 by R1 plus 1 by R2, and there we say R1 R2 by R1 plus R2, okay, like 1 by R1 plus 1 by R2, that is my 1 by R, so that will become R1 R2 divided by R1 plus R2, easy to calculate, okay, like 2 resistors like this. Let us take R1 R2. So here I will say 1 by R parallel is equals to 1 by R1 plus 1 by R2, and there I can say R parallel is basically equal to R1 R2 divided by R1 plus R2 directly. So calculating that becomes easy for us. Simple thing. I hope you are able to understand. Make sure when you are getting these topics, you put your feedback in the comments, whether you are able to understand this, which question you are able to solve or not. If there is any difficulty in any question, you can put all those things in the comment section, okay, so that we can reply also. Now coming to some questions for series parallel combination. In the given figure, R1 is given 10 ohm, R2 is 8 ohm, R3 is 4 ohm, R4 is 8 ohm, battery is ideal 12 volt, equivalent resistance of the circuit and current supplied. Now here you see which are in parallel. R3, R4 both ends are connected parallel, okay. R2 and R4 also parallel, both ends are connected. So I can say R2, R4 and R3, these are in parallel combination, okay. These are in parallel combination, these three. And the equivalent of these three, or I'll say the combination of these three, is in series with R1, because R1 and these three are in series combination. So when you have to find equivalent here, so first find the equivalent of these three. These three are in parallel, so find the equivalent of this. So let us take the equivalent of this is R dash. So 1 by R dash is equal to 1 by R2 plus 1 by R3 plus 1 by R4. 1 by R2, 1 by 8 plus 1 by R3, 1 by 4 plus 1 by R4, that is also 1 by 8. So this becomes 1 by 4 plus 1 by 4, that is 1 by 2. So R dash comes out to be 2. So this is 2 ohm. Now this 2 ohm is in series with R1. Therefore I will say R equivalent, this is this R1 plus 2. What is R1? R1 was 10. So 10 plus 2 is 12. Equivalent resistance we got as 12 ohm. We want to find the current I here. So I is equals to V by R. V is 12. R equivalent is 12. So this becomes 1 ampere. So I will say that is 12 ohm and 1 ampere. That is option D. Now such questions are asked in mains. You may say, sir, this is very easy, very simple. Are they really asked? They are asked. You see, this is January 2023. Previous question was in 2024. So these easy, simple questions are asked in mains, and this particular topic, current and electricity, is very much asked actually. Very much asked. You will see questions will be there for sure, and such easy, simple questions. Current and electricity is a topic in which, like, it's very difficult to make mistakes. Very difficult. Like, you cannot make mistake. Very easy, very simple things are there. Very straightforward, fundamental things are there. In the given circuit, the equivalent resistance between the terminal A and B. Now here you see, we need to find equivalent resistance. But the thing is, here this is short circuited. Short circuited means here the potential difference becomes of this point and this point is same. So here the potential difference is 0. So if potential difference across 2 ohm is 0, current will pass through 2 ohm or not? No. Same, this 4 ohm and 4 ohm, potential difference is 0, current will not pass through this. Current will only pass through this short circuit wire. Okay, so we need to remove this and remove this because no current is passing through them. Now you see, this 2 ohm and this 2 ohm, they are in parallel, both ends. If you connect this end here, okay, it's the same thing. So this 2 ohm and this 2 ohm are in parallel, this and this. The parallel combination of these two will give us 1 ohm. 1 by 2 plus 1 by 2, that is 1. Okay, so this is 1 ohm. Now this 1 ohm, this 3 ohm and this 6 ohm are in series. So I'll say R equivalent here as this 3 ohm plus, here I got this as 1 ohm plus this 6 ohm. 6, 3, 9 plus 1, 10. So equivalent I got as 10. What easier question can be, you can say, as compared to this question? And in mains, if you find like questions are asked from this topic, I'm again and again saying, so many questions are asked from this particular chapter, so many. At least as I already mentioned that 3 questions, even 3 questions are asked. At least 2 questions will be there in your paper. And the level of those questions, if you see mains 2025, you see mains 2024, the level of the questions are very easy from this particular topic. Another question, equivalent resistance of the following network. Here you see these two ends are connected, short circuited it is. If it is short circuited, no current will flow through this. Now this 2 ohm becomes in parallel. So this and this parallel, equivalent is 1. This one is in series with 2. 2 plus 1, 3. So this whole becomes 3. Now this 3 ohm and this 3 ohm are in parallel. So what it is? 3 by 2. Okay. But wait a minute. This 3 ohm and this 3 ohm. 3 resistors are there. All 3 are in parallel. So when I say 1 by R equivalent, so that is 1 by 3 plus 1 by 3 plus 1 by 3. So from here R equivalent comes out to be 1. Okay. R equivalent comes out to be 1 ohm. Now let us talk about battery and EMF. What basically a battery is? Generally the device, the batteries which we have, lithium batteries. So there is a chemical inside the batteries. The chemical energy is converted into the electrical energy by the battery. Okay. So this is, you can say, the actual my battery is, there is some you can say electrolyte is there. Okay. If you talk about like the bigger batteries that we have at homes, inverter batteries. Okay. So there what we have, there is liquid inside. Okay. Electrolyte is there, and there one positive terminal, one negative terminal. Okay. Cathode and anode are there, and this whole behaves like a battery. Now what we need to understand from here, we need not go into the deep like how it is basically working. The equivalent of this is this. This is how we represent the battery. There is a EMF of the battery and there is some internal resistance also, because when the charges will move here, there will be some resistance to the charges also, although that resistance is low. So here we represent the battery, any battery like this. There is a EMF of the battery and there is an internal resistance of the battery. So this is my EMF of the battery and this R is the internal resistance. This R is inside the battery only. It's not that we are connecting it. Sometimes somebody understand like that. No, it is of the battery. Therefore, we say that this is internal resistance of the battery. So any real battery when we represent it like this. EMF is there, internal resistance is there. But sometimes in questions you see just the battery is connected. There is no internal resistance of the battery mentioned there or shown there. So that is an ideal case. Ideally, we say that the battery is there, there is no resistance of the battery. That is an ideal case. But in questions, if the internal resistance is given, we need to take that resistance as well. Now let us discuss about the potential difference across a battery when the battery is charging or battery is discharging. Battery is there, E is EMF, R is resistance. If I ask you what is the open circuit potential across the terminals, open circuit means the circuit is open. Now I connect an ideal voltmeter here. Okay. Then I ask you how much EMF or the potential across these 2 points are there. You will say that potential comes out to be E when the current is not flowing. That is the open circuit potential. So EMF is basically the open circuit potential across the terminals of the cell. Now I connect a resistance. Let us take. I connect a resistance R. Here battery will supply current. So which condition it is? Discharging. So this is my discharging condition. How much potential is there across this resistance R? Or I can say how much potential is there across the terminals of the battery, the same thing. Okay. So here the current is flowing like this. The current is flowing like this. EMF is E. Some potential drop will be there across the resistance R. So what is that? That is IR. So across the terminals, if you see, the potential will be E minus IR. This is my terminal potential. You can write I. What is I? EMF divided by the total resistance. You can put it here. So when the current is supplied by the battery, the terminal potential is lesser than EMF of the battery, isn't it? Yes. The current will increase, the terminal potential of the battery will decrease in this case. If I talk about the other way, let us take, we are charging the battery. Charging the battery means we are supplying current to the battery. Second condition I am talking about, charging. Charging means we are supplying current to the battery. Let us take, maybe with the help of some other battery or some other source like that, and the current is given to the battery. So current goes like this. So in this particular case, what happens is, if you write the potential across AB, so what it will be? It will become E plus IR. Here energy is given to the battery. Okay. Here energy is given to the battery. So if you write the terminal potential across A and B, okay, I'll tell you in Kirchhoff laws how basically we write. Here you see we are going from positive to negative terminal. So this is a potential drop, and here resistance is there, again a drop. So total, if you see, the drop that happens is E plus IR in this particular case, if the current here is I. Okay, so in charging case, what happens? The terminal potential is greater than the EMF of the battery. When the battery is charging, terminal potential is greater. When the battery is discharging, the terminal potential is lesser. Let us do some questions. In the given circuit, the terminal potential of the cell is, what is the terminal potential of the cell? Is this charging or discharging? This is charging or discharging? This is discharging, isn't it? There is no other source. We are not supplying any charge, any current to this battery. So this battery is discharging. That is that we got. So if that is discharging, I'll say V terminal is E minus IR, where I is the current. So current will be like this, supplied by the battery. How to find this current? We need to solve this circuit to find the current. 4 ohm and 4 ohm are in parallel combination. What is the equivalent? Equivalent is 2. The equivalent of this is 2 ohm. Now this 2 ohm and this 1 ohm are in series. So the current, when I say this, this should be 3 volt. This should be 3 volt here. Okay. So I, when I say, that is the potential here, V divided by the total divided by the V or EMF, I can say. The EMF of the battery, that is 3, divided by the total resistance, that is 2 plus 1, that is 3. So this comes out to be 1 ampere. Current we got 1 ampere. I'll put 1 ampere here. So E is 3 minus IR. I is 1 into R. The internal resistance is 1. So this comes out to be 2 ohm. Not ohm, 2 volt. That is option A. Now it may happen that in a circuit there are 2 batteries. Okay, let us take if there is another battery here, and that battery is, let us take, charging this battery. How will we get to know whether it is charging or discharging? Solve for the current. If the current is moving in this direction from positive terminal, the current is entering, it means the battery is getting charged. So that you can identify. Now coming to Kirchhoff laws. So first law, that is law of current. If you take any junction in a circuit, let us take multiple wires are connected at a point. So at any junction, whatever current is coming, the same amount of current will be going. Or in simple words, I'll say that the total charge will be conserved. Whatever charge is coming to the junction, same charge will be going away from the junction, isn't it? Like The charge cannot be created or you can say destroyed. Okay. So at this junction, whatever current is coming, same current will be going away. So when you are writing Kirchhoff law, the current law at any junction, so you write first whatever the total current that is coming. So I2 is coming, I1 is coming. So I will say I1 plus I2. This is I2, I2 is coming, I1 is coming. Now how much current is going? I3 is going and I4 is going. So it is equals to I3 plus I4. This is how we write it. Next is the voltage law. Voltage law suggests that if you move in any closed loop, the algebraic sum of the potential will be 0. Here you need to take care of the sign of the potential, whether there is a potential drop or a potential gain. Let us take this particular circuit. I am considering here the current is flowing like this, I. Now when you move across a resistor in direction of the current, the potential will drop or gain? Potential will drop, we know. In direction of current, if we move, the potential will drop across a resistor. Across a battery, when I am moving, how will I write whether it is gain or drop? If I am moving from positive terminal to negative terminal, there is a drop. If I am moving negative terminal to positive terminal, negative to positive, gain. Positive to negative, drop. Getting it? Okay. Let us take, I am moving in closed loop, starting from this point. We will come back to this point. First of all, this resistor is there. I am moving in the direction of current, there is a drop. So I will say potential drop is minus I current into R2. V is equals to IR for the resistor. Therefore, I am saying drop as IR2, because this is a drop, a negative sign is there. Now, a battery is there. I am moving from positive to negative of the battery. Is it a gain or a drop? Drop. Positive to negative, a drop. So minus V2. For this, a drop, minus IR3. For this, a drop, minus IR4. For this battery, gain or a drop? Gain. We are going from negative to positive, a gain, plus V3. Here, moving like this, in the direction of current, drop, so minus IR5. Then a battery, negative to positive, drop or gain? Gain, plus V4. Then again a battery, again, plus V1. Okay, again. And then this R1, again a drop, so minus IR1. I reach back the same point. Total algebraic sum here is 0, equated with 0, like this. And from here you can solve for I. This is how we apply. Now you may ask, sir, is it compulsory that we need to move in clockwise direction only? Can we move in anti-clockwise? Yes, you can move. You can move in anti-clockwise. All the signs here will be reversed. Equation will remain the same. So you can define the direction, in which direction you can move. Which one is easier for you or you think is quicker for you, you can choose that. And also, like let us take multiple loops are there. Okay, there you can write for each loop you can write the equations in the same way. Getting it? Is this point clear? Only thing is there, the most important thing here is you need to take care of the sign. That is the only problem. Many times what happens, student commit this mistake. They are moving opposite to the direction of current in a resistor and they'll write it negative. That is wrong. When I write the same equation in anti-clockwise way, let us take I am moving from here. R3 is coming, I am moving in the opposite direction through the resistor. It will be a gain plus I into R3. Battery thing will remain the same, like you need to see. You are going from negative to positive or positive to negative. Confusion happens in case of resistor. So whether we are moving in direction of current or we are moving in opposite direction of current, that is very important. You need to check that. Now current division, let us take a current I is coming here and in a circuit, two resistors R1 and R2 are there. How this I will be divided? Let us take I1 is through R1, I2 is through R2. So I will say the potential across these two resistors is the same. So I will say I1 into R1 is equals to I2 into R2. So basically I1 by I2 is equals to R2 by R1. Current is divided in opposite ratio of the resistance when resistance are in parallel. Opposite ratio of the resistance. So if I need to write I1 in terms of I, you can write I as I1 plus I2 and solve that way also, but I can directly write opposite ratio of the resistance. Opposite ratio of the resistance. If I write I1, so R2 divided by R1 plus R2 into I2 is R1 divided by R1 plus R2 into I. Opposite ratio of the resistance. Now coming to the questions. Now sometimes in Kirchhoff laws, when we need to apply, sometimes question comes which are a bit lengthy. You need to write multiple equations and those equations might be lengthy and may take time to solve. So there you need to be smart. Either you can avoid such type of questions for that particular instant, although the question is very easy, but we know it will take time, we'll solve it later, or you may use some different technique. I'll discuss some different techniques also. Using that you can solve, like nodal analysis and other things. Let us solve this question. In the figure shown, the current in the 10-volt battery is close to. Okay, in 10-volt battery, we have to find how much the current is there. How to solve it? We need to first consider the currents. Let us take this current as I1 and this current is I2. So here I1 will come, here I2 will come. I'm using junction rule at this point. So this current, this is total incoming current. So outgoing current should be equal to the sum of the incoming currents, I1 plus I2. I wrote it now. This will be I1 here. This will be I2. Now I need to write the loop rule. Let us move in this loop. Starting from which point? Any one of the point. Let us start from here. Starting from here, drop in the direction of current minus 5 I1. Drop in the direction of current minus 10 I1 plus I2. Drop in the direction of current minus 2 I1. Gain, because I am moving from negative to positive, so plus 20. This is equal to 0. This is my first equation. Now second equation for this loop, let us move from any one of the point. From here I am moving like this, or let us move in the direction of current. I generally prefers the direction in the direction of current. Okay, so I'm moving from here. So first drop, so minus 10 I1 plus I2. Okay, minus 10 I1 plus I2, then minus 4 I2. Then we are having plus 10 and this is equal to 0. Two equations are there and two variables are there, I1 and I2. We can very easily solve it. How we should solve it? I need to find I2. So from one of the equations, I will replace, I'll put or I'll find I1 in terms of I2 and put in the other equation. Let us write in this second equation first. From this equation, I can say 10 plus, what is this? 10 plus 4, that is 14 I2. Okay, so 14 I2 and plus 10 I1. This is my 10. With 2 I can cancel. So this is 5. This is 5. This is 7. So from here I can say that I1 is basically 5 minus 7 I2 by 5. Perfect. Is it correct? 5 minus 7 I2, yeah, by 5. This is my I1 and this I1 I will put in this equation. Let me use different color for that. Now in this equation, let us simplify it first. How many I1 is there? 10 plus 5, 15 plus 2, 17. So minus 17 I1. Minus 17 I1 and minus 10 I2. Let us take on the other side, and this is my 20. From here I will put I1. I1 is 5 minus 7 I2 by 5. This is I1 into 17 plus 10 I2. This is my 20. From here I will find I2, and now if my I2 comes positive or negative, if I2 comes positive, it means this is the direction. If I2 comes negative, it means the direction is opposite, and here in this particular case this will come out to be negative. So you need to check that. Okay, you can check that. Don't believe in my words. Solve the equation, check whether I2 is coming out to be positive or negative. If it is positive, it is moving in this direction. If it is negative, it is moving in the opposite direction. That is the meaning of positive negative sign in this particular case. So solve this equation, put your answer in comments. Make sure you put your answer in comment section which option here is correct. Moving to next question. The current flowing through 1 ohm resistor is N by 10A. The value of N is. Okay, now another case. Here we need to find the what is the current that is flowing through 1 ohm resistor. This 1 ohm resistor here. How to solve it? Three loops are there. Okay, we can write three equations. Three variables will be there. We can easily solve. How to consider that? This is I1. Let us consider this as I2. This I am considering as I2. So what it will be in this direction? In this direction it will be I1 minus I2. How I wrote it? Junction rule. I1 minus I2 I got. I2 is there. Let us consider I3 here. So this will become I2 plus I3 here. And I2 plus I3 is there, and this is I1. So what it will be here? I2 plus I3 minus I1. I2 plus I3 minus I1 is flowing in this. So in all the branches I will say I have mentioned the current. Now moving in the loops, writing the equation. I will move in this loop, write the equation. Let us start from point A. Let us check if I did any mistake here in writing. This is I3 as well. I hope everything is fine. Okay. In this loop, if I write, so I am starting from point A. So this will become minus 4 I2 in the direction of current. Then minus 2 I2 plus I3. Then minus 1 into I1. Okay, minus 1 into I1. Here the current is I1. Minus 1 into I1 and plus 10. And this is equals to 0, first equation for the first loop. Now for the second loop, let us move like this, starting from point A. So minus 4 into I1 minus I2. Okay. Then moving through this, so plus, we are moving in opposite direction of the current. So plus 2 of I2 plus I3 minus I1. Then moving across this, so this is moving in the direction of current, so minus I1 plus 10 is equals to 0, is equals to 0. This is my second equation. Third equation, let us move in this loop. Starting from point D, let us take. So plus 5, then minus 2 into this I2 plus I3, then minus 2 into I2 plus I3 minus I1, is equal to 0. I completed the loop is equal to 0. This is my third equation. Okay, this is my third equation. Three equations we have, three variables we have. We can solve for I1, I2 and I3, and we need to answer, we need to find I1. Okay, from here you can solve these equations. Make sure you comment your answer in the comment section. Now, also in between the class, as you are watching the video, you may be having some conceptual doubts, okay, in any particular topic that I am discussing. So if you are having that, make sure you mention that in the comment section. We will take those questions as well, okay. So I'll respond that. Okay, as shown in the figure, a network of resistors is connected to battery of 24 volt with an internal resistance 3 ohm. Here internal resistance of the battery is given, so we need to consider that. The current through the resistor R4, R5, I4 and I5, R4, R5, I4, I5. The values of I4 and this should be I5 here and I5 are, okay, I4 and I5 we need to find. First of all, let us find the total current basically, because that total current is only divided into two parts here. So first of all, let us find total current. For total current, I need total resistance. 2 and 2 in parallel, equivalent is 1. 1 plus 2 is 3. Okay, 1 plus 2 is 3. 20 and 5 are in parallel. These two are in parallel. Equivalent will be 20 into 5 divided by 20 plus 5. That will come out to be 4. So this equivalent is 4. This equivalent is 4. And this is 2. So 2 plus 4 is 6. 6 plus 2, 8 plus 1, 9. And this 3 is in series only. So 9 plus 3, 12. Okay. 2 plus 4, 6 plus 2, 8 plus 1, 9 plus 3, 12. So R equivalent is total resistance is 12 ohm. So total 12 ohm. Total current if I write, that is total battery, that is total EMF here, that is 24 divided by 12. What is that? 2 ampere. So 2 ampere current is coming. Now this 2 ampere current is divided into two resistors connected in parallel. The current will be divided in opposite ratio of the resistances. So if I write I4 will be R5 divided by R4 plus R5. Into the current I. Let us write this. R5 is 5 divided by 5 plus 20, 25 into the current I is 2. So this is 5. This becomes 2 by 5. Now 1 is 2 by 5. Another will be subtract from 2 either, okay, or again write the ratio. So that will become 8 by 5. So 2 by 5 and 8 by 5. That is option D. This question was very easy. Now, as I mentioned, like in Kirchhoff law, there can be some questions which are lengthy. There you need to write, as I did previously, you need to write equation. Solving the equation will take some time. Either you are very smart by saying like, is there any additional other way to find that, like nodal analysis or some other things, or if you have to go from that method only, it will take time. Anyhow, you cannot avoid that. A current of 6 ampere enters at one corner P of an equilateral triangle PQR having 3 wires of resistance 2 ohm each, leaves by corner R. The current I1 in ampere is. What is I1 here? You see, 6 ampere is coming. Here how much will come? 6 ampere only. Till here 6 will come. Now this 6 is divided into two parts, I2 and I1. This total is how much? 4 ohm. This is 2 ohm. Current will be divided in opposite ratio. I need to write I1 here. So this resistance is 2, this resistance is 4. I1 will be equal to opposite ratio, 2 divided by 2 plus 4. Opposite ratio, isn't it? This is I1. So this resistor is R2. So that resistor divided by the total resistance into the total current, that is 6. So that comes out to be 2 ampere. Okay, easy. Yes, that is easy. Now we are going to discuss few of the methods you can use that will help you to simplify the things in a very easier way. Uh, if you are saying that, sir, I am going to use that method only, whether it takes time or not time, that is not my issue. So if that is there, that is okay. But nodal analysis will save time in few of the cases, not always. It's not that you can use this method always. In few of the cases, it's not very helpful to use nodal analysis. Let me give you an example. Let us take this example. Okay. R1, R2, R3, V1, V2. If I ask you solve this, find the currents, what you will do? Write the two equations, move in the loops, you'll solve it. Another way I am saying is, let us take, this is grounded. Grounded means zero potential. Consider the point of that particular at this particular point at 0 volt. Okay. Will this change? Will this make any change in the circuit? No. Why I considered it? Such that I defined one point as my reference. I can write the potential of other points with respect to that. So this I am considering as 0. Let us take this potential as V. This current I1, this current I2, this current I3. I1 plus I2 plus I3 is 0. Total incoming current is 0. Total outgoing current should be 0. What is I1 now? So I1, if I write, I1 is the current through this. You see, this is at 0 potential. This is V1 now. So plus V1. So this is at potential V1. This point is at potential V1. So what will be I1? I1 will be V minus V1 divided by R1. So V minus V1 divided by R1. What is I2? I2 is, this is V, this is 0. Potential across this resistance is V minus 0 divided by R2. What is I3? This is 0. So this is minus V2 here. Potential across resistance R3 will be V minus V2 divided by R3. Okay. So I3 will become V minus of my V2 divided by R3. Wrote it. Now I1 plus I2 plus I3 is equals to 0. From here you will get V. After getting V, you can write and solve. It may help in some of the cases when there are more loop equations and where the nodes are less. Like here, if you see, if let us take multiple nodes are there, here I can consider one as reference. Therefore, I am writing this equation. But let us take, there are multiple nodes. One I will take reference, but another potential also I need to define. Okay, I cannot write directly as I wrote in this case. Because this was 0, I wrote this as V1 directly. This was 0, I wrote this as minus V2 directly. But if a bigger circuit is there, so in nodal analysis also it may take time. Okay, it may not be very helpful also in some particular cases to use nodal analysis. Now, let us see this question. Here, this is the condition, we need to find V. Now, what I can do is, this is grounded, this is V, this current I am considering as I1, this is I2, this is I3. I know I1 plus I2 plus I3 is 0. What is I1? I1 will become V, this is 0, this is 2 volt, this is 0, this is 4 volt, this is 6 volt. So, this is V0, okay, here. So, I1 will be V0 minus 2 divided by 1 kilo ohm. This is I1 plus I2 V minus 4, V0 minus 4 divided by 1 kilo ohm plus this V0 minus 6, V0 minus 6 divided by 1 kilo ohm, and this I1 plus I2 is equals to 0. Anyways, this 1 kilo ohm will go to the other side, and from here I will say that V0 comes out to be 6 plus 4, 10 plus 2, 12 divided by 3, that is 4. 4 volt. Now in such questions it is very easy. Otherwise, if you go from Kirchhoff loop rule, let us take, okay, you'll consider current here, I1, I2 currents you'll consider, you'll move in this loop, you'll move in this loop, you'll get two equations, two variables, then you will be solving, and then eventually you will get what is the potential V naught there. So it is a bit longer way to do. Therefore, I am saying here nodal analysis is very easy. It will like just take few seconds to write. Quickly you can write, just see and write this equation. Okay, Wheatstone Bridge. Now, Wheatstone Bridge is a condition when, let us take, this resistance is R1, this resistance is R2, this resistance is R3, this resistance is R4, and let us take here some potential is applied across them. And I have connected a galvanometer. Galvanometer is used for current detection purpose. This is galvanometer. And what will happen? Some current will be there in galvanometer. Galvanometer will be showing some current. Now, at a particular condition, what happens? This bridge becomes balanced. And at that balanced condition, this galvanometer will show zero deflection. That we say that the bridge becomes balanced. Zero deflection means current through the galvanometer will become zero. When the current through the galvanometer will become zero, when these 2 points will have the same potential, isn't it? Galvanometer is having some resistance. When current through a resistance is zero, both the points across the resistance will have the same potential. So when these 2 points will have the same potential, what will happen? The current through this zero. When that potential same will happen, let us take. I am considering this current to be I1, this current to be I2. So if this current is zero, so this will be I1, this will be I2. Here this point is having same potential, these 2 points are having same potential, so this drop is equal to this drop, so I will say I1 R1 is equals to I2 R2. Similarly, these 2 points are connected here, so this point and this point is having same potential, it means drop across R3 and R4 is same, so I1 R3 is equals to I2 R4. If I divide these, I'll get R1 by R3 is equals to R2 by R4, or I can write it other way, R1 by R2 is equals to R3 by R4. Any of the way you can write it. If the ratio of these two resistance is same as the ratio of these two resistances, or the ratio of these two resistance is same as the ratio of these two resistance, the Wheatstone bridge is at balance condition. These 2 points are having same potential. You may connect these 2 points. Same potential means you can connect that. No difference. Even they are not connected, they are having the same potential. You can connect them. Connecting means the same potential. Current through this will be zero. Now what will happen in a particular case? You might be given a balanced condition and a resistance is connected here in place of galvanometer. And they may ask you what is the current in the circuit, what is the equivalent resistance of the circuit, these type of questions. And that check whether the bridge is balanced. If the bridge is balanced, remove the middle resistance. If the bridge is balanced, remove it because that is not conducting. Current is zero, remove that. Then you can solve that very easily. It will show some questions to you. Say this. A battery of 6 volt is connected to the circuit as shown below. The current I drawn from battery is. What is the current I? Now you may say, sir, solving this is a very lengthy process. Consider this current and move in this loop, one this bigger loop, 3 equations will be there, 3 variables will be there. Solving will take you at least 10 minutes. But 3 by 6, 3 by 6. 3 by 6 is equal to 3 by 6. These 2 points will have the same potential. If the potential is same, I will remove this resistance, 5 ohm. Remove this 5 ohm resistance, what will happen? Circuit becomes very simple. Circuit becomes very simple. These 3 are in series, these 2 are in series. What is that? 3 plus 3, 6. These are in series, 6 plus 6, 12. 6 and 12 are in parallel. 6 into 12 divided by 6 plus 12, that is 18. 4 ohm. I directly got this equivalent resistance to be 4. 4 plus 2 is 6. So R equivalent becomes my 6. Total resistance of the circuit, I will be 6 by 6, 1 ampere. V by R equivalent, this is my 6 by 6 and this comes out to be 1 ampere. So the current is 1 ampere. Very easily I am able to write. And trust me, in mains if such question is coming, where you see 3-4 resistors connected like 5 resistors connected like this, most probably that will be a balanced Wheatstone bridge condition only. That is not going to be anything different. Why so? Why so? Because they will not ask you such a question in which so much time will be taken. They will ask you only easy question only. So that's I'm saying it may not be balanced. You see whether it is balanced or not. I'm not saying that don't check. I'm saying check it. But 90% it will be a balanced bridge condition only. Therefore, when you see such a question, first check it whether this is a Wheatstone bridge condition balanced or not. If it is balanced, you can solve that in few seconds. Okay, now this is another question. Now I am giving you this question. See this whether this is balanced or not, and read this question accordingly, solve it. I think what they are asking, the potential difference B and D should be 0. Okay, it means this needs to be balanced, and for that condition you need to find the value of X. So solve it, write the equation, then solve it. I hope you are back after solving it. Make sure you put your answer in comments. Now let us discuss. 6 and 3 are in parallel, equivalent is 2. 6 into 3 plus 6 plus 3, 9. Okay. So 6 into 3, that is 18 by 9 is 2. Therefore, this is 2. This total is 3. Both are in series. This is X. This is parallel. So I can write this as X into 1 divided by 1 plus X. So X divided by 1 plus X. Okay. B and D should have same potential, means this resistance by this should have this by this equal to. Okay. So 2 by 3 is equal, so this resistance, that is X divided by 1 plus X, this resistance by X, so by X here. Now solve for X. This X got cancelled, so this is 2 plus 2X, this is my 3, X comes out to be 1 by 2, X comes out to be 1 by 2, 1 by N becomes 2. Very easy question. Wheatstone bridge questions are very easy always. Now infinite ladder circuit. Sometimes not in mains actually. Infinite ladder thing is not asked in mains. But I am telling you a concept because that will make a better conceptual clarity for you. So sometimes you may find a question in which some part of the circuit is repeated again and again and again like that. So therefore that is continuing till infinity. Let us take an example. 1 ohm, 2 ohm, 1 ohm, 2 ohm, 1 ohm, 2 ohm, like that circuit is continued. And now you need to find what is the equivalent resistance of this. I am saying that if the equivalent of this whole is R equivalent, the equivalent of this will also be R equivalent. Okay, this, because this is also the same circuit, so equivalent of this will be R equivalent. So I can say this 1 ohm, this 2 ohm, and this is my R equivalent now, and this combination will have a resistance equal to R equivalent. So write the equation. Now this 1 ohm in series with these two parallel. Okay, what these two parallel means R equivalent into 2 divided by 2 plus R equivalent, that is in series with 1, so plus 1, and this is equal to R equivalent only. So equal to R equivalent. From here we can solve for R equivalent. Okay, this is how we can very easily write this equation. Same part is repeated again and again. I got this whole is same as this whole. Okay, so this is R equivalent, total is also R equivalent. Considering this R equivalent, I connected here, and combination of this should also give R equivalent only. Now I wrote the equation, got the R equivalent very easily. Infinite ladder questions are not asked in mains. Symmetric circuits. Now in some of the circuits you may find some symmetricity is there. Let us take whatever the you can say connection are on the left side, same type of connections are on the right side, or you may say like perpendicular symmetricity, horizontal symmetricity in a circuit. Okay, so I'll talk about all those things. So first of all, let us take a symmetricity like this is R, this is R, this is R, this is R, 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 and here you need to find the equivalent circuit. So what we need to do, here we can very clearly see that there is a symmetricity about this line. Which line? Let me draw that line. About this line, the circuit is symmetric. Okay, about this line, the circuit is symmetric. It is also symmetric about horizontal line also. I'll talk about that. So about this line, the circuit is symmetric. The points which are on the line of symmetry, they are having the same potential. So these resistance will not conduct, this will not conduct. And anyway, from Wheatstone condition also we can see that. So you can remove that. Also, you can connect these 3 points with a wire. And whatever the resistance of this on the left half will be same as the resistance on the right half. So just find the resistance of half of the circuit, multiply it with 2. Now these 3 will become in parallel because same potential here, these 3 points will be connected, these 3 are in parallel, so equivalent will be R by 3. This will also be R by 3 only, so just multiply this with 2, so equivalent will become 2R by 3. Okay. Now other way, if I see the symmetricity about this line, then what will change? Which things will change in that particular case? So let us redraw it. This symmetricity is there. If this about this, the line is symmetric, our connections are like this. Okay. So here what you can do is you can fold this. You can fold it. If you fold it, this point will come on this point. Okay. And all these resistors are coming on one over the another. Okay. So they are coming in parallel. So these 3 resistors, this will become half because R parallel with R will become R by 2. So what it will become now, if you fold it about it, this will remain R, this will remain R, this will be R by 2, this is R by 2, this is R by 2, and this will be removed by Wheatstone bridge condition, and then you can say these 2 are in series R, that will become 2R, these are in series R by 2, that will become R, so 2R and R are in parallel, so that will become 2R by 3, which is the same as that. Any one of the way. Sometimes there may be only one symmetry, like only this symmetry, then you can find half resistance, multiply with the other half. Sometimes maybe only this symmetry only. In that you fold the circuit, each resistance, whatever is coming on one top of the other, okay, so that will become half. Now we are having this question, the effective resistance between A and B. I have already discussed such questions, so you can solve this question yourself. Okay, I'm giving you some time. Solve it. I'm stopping here. Okay, you can pause the video. Okay, so solve this, comment your answer, then come back. I hope you are back. Now here again I can say this is the line of symmetricity. Remove this resistance, remove this resistance. These three are in parallel, R by 3. This R by 3 and this R will become 4R by 3. This will also be 4R by 3. Total 8R by 3, 8R by 3. So seeing the symmetricity makes very easy for us to solve a question. If you are able to see the symmetricity in a circuit, now let us take in this, a battery is connected and he is asking you, tell me this current, tell me that current, and then you write loop rules and all, it will take lot of time. But if by seeing the symmetricity you are able to just simplify this circuit very easily. Now whatever he is asking, whether the current he is asking in a particular resistance or potential drop or anything else, you can find very quickly, very easily. Now another question, the equivalent resistance of the circuit shown below between points A and B. Between points A and B, the circuit is symmetric about this point. You may say, sir, but this 16 ohm is coming between. You can take 8 and 8, one of the way. Okay, or what you can do is just solve the upper circuit. This is the symmetricity. This 4 will be removed. 4 and 4, 8 parallel with 4 and 4, 8. 8, 8 parallel will give you 4. That 4 and 16 are again in parallel. So 16 into 4 divided by 4 plus 16. So that will become 64 divided by, this is 20, 3.2 B. Getting it? I found the equivalent of this line of symmetricity, or from Wheatstone Bridge condition also I can say this will be removed, because 4 by 4 is equals to 4 by 4. So this is removed. 4 and 4, 8. 4 and 4, 8. 8 parallel with 8, 4. 4 and 64 in parallel. 4 and 16 in parallel. So 4 into 16 divided by 4 plus 16, 64 by 20, that is 3.2. Now we are going to discuss the combination of cells, grouping of cells basically in series and parallel. So let us talk about first the series combination. Cells topic is also very much asked. So this is also, I will say, important topic. Series combination means two cells are connected in series. Now connections may be of two ways. The terminals, positive terminal is connected with positive, or positive is connected with negative. Okay, so the combination can be like this, or the combination can be like this. You may say, sir, why you are not drawing internal resistance here? Sometimes we specifically show internal resistance, sometimes we don't, so we just write here. So here I'll say this is E1 comma R1, this is E2 comma R2. E1 R1 E2 R2. Now here we are considering equivalent of this, means like this. This is my E equivalent, internal resistance R equivalent. Similarly here this is my E equivalent, internal resistance R equivalent. Now in this particular case, how to find basically E equivalent and R equivalent? This is what we need to do. Now one thing is, if I write the equation, let us take here current that is flowing is I in this particular direction. So if I write the potential across these 2 points, so what it will become? I'm considering this as, you can say, my reference 0, and this you can consider V. So from there if I write, so it will become plus E2 minus I into R2, here plus E1 minus I into R1, and that is equals to V. So V will become basically E1 plus E2 minus I R1 plus R2. Okay, that will become here. Now, and this V is equals to my what? E equivalent minus I into R equivalent. So I got my E equivalent is basically E1 plus E2. This is E1 plus E2. And what is R equivalent? R1 plus R2. Okay. And here if I write that, potential is V, current is flowing I here, and here if you try to write the potential V there, so V will come out to be E1 minus E2 minus I into R1 plus R2. And so this will become my E equivalent. R equivalent is R1 plus R2. R equivalent will not become R1 minus R2 when it is the polarity is connected opposite. Only E will change. E will become E1 minus I2, but R equivalent will become R1 plus R2 only. That's the difference. Okay, now parallel combination, same cells connected in parallel with each other. Now we need to write, I am considering this whole as my E equivalent and R equivalent. If I write current here I, okay, so here if I write the terminal potential, let me write V, okay, I am taking current in this direction, this. If I write VAB, what is that? That is E equivalent minus I into R equivalent. In this particular case, this current is I, this current I1, this current I2, and this current I3. And I can say I is equals to I1 plus I2 plus I3. I3. What is I1? If you write from here, the VAB is my V. So VAB is basically what? E minus I1 into R1. E1 minus I1 into R1. From there you can write I1. I1 is E1 minus VAB divided by R1. E1 minus VAB divided by R1. Putting I1 here. E1 minus VAB divided by R1 plus I2. E2 minus VAB divided by R2 plus I3. E3 minus VAB divided by R3, and this is equal to I. Okay, from here further if I simplify, it will become E1 by R1 plus E2 by R2 plus E3 by R3, and this is VAB by R1, VAB by R2, VAB by R3, whole I am taking on the left, dividing with 1 by R1 plus 1 by R2 plus 1 by R3, minus I divided by 1 by R1 plus 1 by R2 plus 1 by R3. So this whole expression is becoming like this. So I can say this is my E equivalent. This is my E equivalent, and 1 by this of will become my R equivalent. So from here if I write 1 by R equivalent, this is basically 1 by R1 plus 1 by R2 plus 1 by R3, and similarly this is my E equivalent. So E equivalent by R equivalent if I write, this is E1 by R1 plus E2 by R2 plus E3 by R3. You need to remember this. For parallel combination, 1 by R equivalent is equals to 1 by R1 plus 1 by R2 plus 1 by R3, and E equivalent by R equivalent is equals to E1 by R1 plus E2 by R2 plus E3 by R3. If the polarity in between is opposite, let us take E2 is connected opposite, so I'll consider a minus sign for E2 here. Okay, accordingly, whichever polarity is opposite, you consider negative sign in front of that particular EMF. Clear? Okay, great. Let us solve this question. Two cells are connected in opposition as shown. Cell E1 is of 8 volt EMF and 2 ohm internal resistance. 8 volt and 2 ohm. Cell E2 is of EMF 2 volt and 4 ohm internal resistance. The terminal potential across E2 is, across E2, how much is the terminal potential? Which one is greater? These are connected, by the way, in opposite sense. So 8 volt is greater, so effectively I'll say that current will move in this direction. So current will go in this direction. So current will go in this direction, it means it is charging. If it is charging, the potential across this will be E plus IR. Okay, so V is equals to E2 plus I into R2. What is I, by the way? To write I, either I can move in the loop and write the Kirchhoff loop rule and write the equation, or directly I can say I is equals to my total EMF. Total EMF will be 8 minus 2, because opposite sense, 8 minus 2 divided by total resistance in this loop. How much? 2 plus 4, 6. So this is 1 ampere, 1 ampere. 1 ampere. Put I as 1 ampere here. E2 is 2. Okay, E2 is 2. So 2 plus 4 into 1. Is it right? 2 plus 4 into 1, this becomes 6. 6 volt. This, when I'm moving from this to this, the drop, across, I'll say the cell, the drop is there, and across the resistance also the drop is there. Therefore, they are combining. So E2 plus I2 R2, or directly I say that the cell is charging. So directly I can say V terminal is E2 plus I into R2. So E2 is 2, and I got from here as 1, and R2 was 4. So this becomes 6 volt. So the answer comes out to be 6 here. Okay, another question. Two identical cells, each of EMF 1.5 volt, are connected in parallel across a parallel combination of two resistors of resistance 20 ohm. What he is saying, two resistors of 20 ohm are in parallel. Okay. Now, two identical cells, each of EMF 1.5 volt, are connected in parallel. This cell and this cell. This is 1.5 volt. This is 1.5 volt. Okay, some internal resistance will also be there. The voltmeter connected in the circuit measures 1.2 volt. It means here if we connect a voltmeter, which will give us the potential across these 2 points, this is 1.2 volt. Okay, the internal resistance of the cell is, so I need to find what is the internal resistance here. First of all, this 20 are in parallel. Put a 1 resistance, that is 10 ohm. Another thing, these two cells are in parallel. You can replace them by the equivalent. So how to find the equivalent? First of all, find the R equivalent. 1 by R equivalent is equals to 1 by R1, that is R, plus 1 by R2, that is R. So this is 2 by R. So R equivalent comes out to be R by 2. Now let us find E equivalent. So using the second formula, E equivalent divided by R equivalent, that is R by 2, is equals to E1, that is E, divided by R1, that is R, plus E2, that is E, divided by R2, that is R. So 2 E by R. So from here I got E equivalent as E only. only the resistance will become half. So I am redrawing this circuit. This is equivalent 1.5, the resistance R by 2. Now there is a 10 ohm resistance in parallel here. Okay, equivalent of these two 20. Now we need to find the potential across the cell, or you can say across the 10 ohm. Okay, cell means across the terminals here. So that is given to us as 1.2. How to write that? I can say that is E minus IR. E is 1.5 minus I. What is the current here? 1.5 divided by the total resistance 10 plus R by 2 into R by 2. Okay. And this is given to us as 1.2. How I wrote this equation? I need to write this potential across, or you can directly say across 10 ohm resistance. Either you write this equation, or you can directly say that is across 10 ohm resistance, and how much that will be? That will be 10 divided by 10 into the current. Current is 1.5 divided by 10 plus R by 2. It's the same thing. And this is given to us as 1.2. 1.2. Okay. Now from here 3 into this I can say 0.4, 3 into 0.5. So this will become 5 and that 4. So this is 2 into 2, 2 into 5. This is 25. That is equals to 20 plus R. R comes out to be 5 ohm. R comes out to be 5 ohm. That is C. Okay. Now here first we need to draw the circuit by understanding the question, then we can solve it. Now such type of questions can be done very quickly when you are already clear you need to draw. So just quickly draw it. You can just while reading only you can simplify this 20 in parallel. So just connect 10. Just by reading only you can simplify it. Two cells, equal cells are connected in parallel. E will remain the same. R will become R by 2, and then just write the solution directly. Okay, thermal effect of current. Let us take a current is flowing in a resistance. How much energy will be dissipated per second? That we say the power dissipated across the resistance. That formula we know, that is equals to I square R, or that is equals to VI or V square by R. That formula we know, but let us see how it comes. This resistance is R. A current I is going like this. So in a interval of dt, I am talking about in an interval of dt, how much charge that will pass through it? You will say the charge that will pass dq, that will be IDT. This much is the charge. So how much you can say energy will be dissipated? Energy will be dissipated, that is the potential difference across this into the charge. Potential difference V into dq. What is the potential difference? V. And what is charge? Dq. This is the energy dissipated. Okay, or I can say let us take dH, the heat. This is dissipated as heat energy, so I'm writing that as dH. Now V and dq I can say that is IDT, and this is dH. So from here dH by dt, that comes out to be the product of potential and the current across the resistor, and dH by dt is my power. So my power dissipated across the resistance, PD or just P, let me not confuse you. So P, this is equals to VI, or if I put V is equals to IR in this case, so it will become I square R, or if I put I as V by R, so this will become V square by R. Okay, so this becomes the power dissipated. So you see which variables are given to you, accordingly you can write it. Make sure You are clear with these variables. Sometimes the students are confused. Confusion where? V is not the battery potential, it is the potential across the resistor. Okay, that is the potential across the resistor when you are writing V. So don't get confused with that. Let us discuss this question. An electric bulb of 500 watt and 100 volt is used in a circuit having a 200 volt supply. Calculate the resistance R to be connected in series with the bulb so that power delivered to the bulb is 500 watt. Okay, 500 watt bulb was there. Let me show a bulb like this. It is connected, the rating was given as 500 watt and 100 volt. Means if you connect it to a 100 volt supply, the power dissipated will be 500 watt. This is the meaning of this. 200 volt supply, it is connected with a 200 volt supply, and he is asking how much resistance needed to be connected in series such that the bulb, so that the bulb deliver a power of 500 watt. Okay, it's, if you use your mind here, like what he is saying, that when 100 volt rating is saying that when 100 volt will be across this, the power dissipated will be 500. And he is saying what is the condition for 500? Condition of 500 means 100 volt comes across this, total is 200, and 100 volt come across this, equal across these two resistors. When it will be equal? When my resistance connected is equal to the resistance of this bulb. Okay, so it will happen when R is equals to basically resistance of the bulb. What is the resistance of this bulb? Power is given, volt is given. So I can use formula V square by R is equals to P. From there I can get. So R is equals to basically V square by P. This is the resistance of the bulb. So what is V? V is 100. 100 square divided by P is 500. So this will become 100 divided by 5, which is 20 ohm. Okay, so this is 20 ohm, so this should also be 20 ohm. Okay, so I got this R also to be 20 ohm. That is option A. If you go by default method, like if you are not able to see directly that this should be equal, then you can find the resistance of bulb first. Okay, then write the current in the circuit in terms of this variable resistance R. Then write the power across this, that is I square R, and make that power equal to 500 watt, and there you will get R to be 20 ohm. That way also you can solve it. Next question. The resistive network shown below is connected to a DC source of 16 volt. The power consumed by the network is 4 watt. The value of R is. So total power consumed is given to us as 4 watt. So what I can do? I can find the current, and VI I can do is equals to 4 watt. From there I can find my R value. Okay. So this 4R and 4R in parallel. So equivalent of this is 2R. 6R and 12R in parallel, equivalent of this would be 6 into 12 divided by 6 plus 12R. 3, 4, so equivalent is 4R. Total resistance will become 4 plus 1, 5, 6 plus 2, 8. Okay, 5, 6 plus 2, 8. So total R equivalent is 8R basically. Getting it? Again I am repeating, this is 2, that is in series with this, 2 plus R, 3R, 2R plus 3R, 3R, 2R plus R, 3R, and this is in series with 4R, 7R, series with R, 8R, total equivalent 8R. Now what is the current? Or I need to equate the power, I can just write V square by R. Okay, so power is V square by R, V is 16, so 16 square divided by R, that is 8R, and this is given to us as 4 watt. Okay, now simplifying it, 16 into 16 divided by 8R is equals to 4, 4 into 4, 8 into 2, 4 into 2, 8. So R comes out to be 8 ohm. Perfect? Yes. A option. Power questions are generally simple, straightforward questions till now that are asked in mains. Another question. A resistor develops 500 joule of thermal energy in 20 seconds. Now, here he is talking about energy. If you have to find energy, you will say power into time. Okay. And if let us take that power is variable, then you can integrate P dt. Now, read it again. A resistor develops 500 joule of thermal energy in 20 seconds when a current of 1.5 ampere is passing through it. If the current is increased from 1.5 to 3 ampere, what will the energy develops in 20 seconds? Now, initially the current was 1.5. Energy in 20 seconds was 500. Now, current is going from 5 to 3. It means current is getting from I to 2I. I to 2I. Resistance is the same. What is power? I square R. So if the power is here P, here it is I square R, 4 times of P. So 4 times of 500, that is 2000 joules. Easy? Yes. Bulb used in parallel series and its rating. So sometimes multiple bulbs are given and their ratings are given, and then it is asked which one will be the brightest. So brightest means the maximum power dissipated across that. Okay, so you see which one is having maximum power, or it is mentioned like, let us take find the current through that bulb, find the potential across that bulb. Those things are given. So when the bulb is mentioned, so what it will be given, the rating of the bulb will be given to you, okay, in watt, and the voltage rating will be given to you. Let us take this much volt, as we had in question, 500 watt and 100 volt. So like that. So what you need to do, find the resistance from here. What is the resistance? You can find resistance by using a power. So power is equal to V square by R. V square by R. So resistance is V square by P. So use the rating values to find the resistance, then replace the bulb with a resistance. Now whether the bulb is connected in series, so find the series resistances and then solve it. If they are connected in parallel, connect them in parallel, then solve it. I show you. An electric bulb rated 220 volt 100 watt is connected in series with another bulb that is 220 volt 60 watt. If the voltage across combination is 220 volt, the power consumed by 100 volt is. Okay. Now, first, this is the rating for first bulb. Second bulb, this is the rating. They are connected. If the now if the voltage across combination, yeah, they are connected in series. That is given to us. So that also we need to check. They are connected in series. So if I find resistance of first one R1, what is that? I'll use V square by P. V square by P, because V square by R is P. So V square by P is R. V square 220 square by P 100. So this is 22 square. Similarly R2, V square by P 220 square by 60. Got it? Now they are connected in series. R1, R2, and power consumed by 100 watt bulb will be, okay, how much is the power consumed across this bulb? So you find the current I. How? The battery is given. This is 220. That is given 220. Okay, yeah. So power across this P1, that is I square R1. What is I? I is 220 divided by R1 plus R2 square into R1. What is R1? This is R1. What is R2? This is R2. Now you put the value of R1, R2, solve this question. Let me know your answer in the comments. I'm taking, you can take a pause of this video, solve it, then come back. Okay, I hope you solved it. Put your answer in the comment section. Okay, now moving ahead, maximum power theorem. Let us take some EMF E, internal resistance R. Okay, this is my cell. These are the terminals of the cell. Now I am connecting a resistance R, and it is asked find R such that the power dissipated in R is maximum. Find R such that power dissipated in it as maximum. How you will do? Considering R to be variable, write the power dissipated across R and then see the conditions for that to be maximum. Okay, try to write the equation. You are writing? Okay, let me help you. Let us take here current is I. So I will say I current is equals to my EMF divided by R plus R. This becomes my current. So if I say power dissipated across R, so that is I square R this is the power dissipated. Now what is the condition for this to be maximum? Which one is variable? R is variable. How much that should that R should be? Now for a function to be maximum, I can differentiate that equate to 0. Okay, that is the condition for maxima and minima. So differentiate this power with respect to my variable resistance R. Okay, and then equate that to 0. How to do that? This is one function, this is another function. I'll first keep this outside as it is. Differentiate the second one, whose differentiation will be 1, plus take the second as it is outside, this constant also E square outside as it is. Differentiate this 1 by R plus R square. So differentiation of 1 by x square, how much is that? Minus 2 by x cube. Differentiation of 1 by x square, when I'll differentiate, I'll write this as x to the power minus 2. Its differentiation will be minus 2 into x to the power minus 3. So minus 2 by x cube. So into minus 2 divided by R plus R cube into differentiation of R plus R, that comes out to be 1, and make this equal to 0. If I make this equal to 0, try to simplify from here. E square part, E square divided by R plus R square. Okay, this I'll take common. Is that perfect? Yeah. So this will become 1 minus 2R divided by R plus R. This is equal to 0, so this is equal to this. So R is equals to R. So for the maximum power dissipated across the resistance, the external resistance should be equal to the resistance of the cell. Getting it? Now, what if there are other resistance also? Some other resistance is also connected. Then I'll say my connected, the external resistance that I'm going to connect should be equal to the resistance of the circuit. Resistance of the circuit across these 2 points. Okay, that you can find by short circuiting the battery, and then that you can find. So therefore this resistance across these 2 points should be equal to the resistance of the circuit, then only the power dissipated across that resistance will be maximum. In mains a question was asked on this, and this is the question, and this is just the straightforward question. We got R is equals to R, R is equals to R is the answer. No variation, just say it. A cell of internal resistance R derives a current through an external resistance R. The power delivered by the cell to the external resistance will be maximum when R is equals to R. Remember it, R is equals to R. Now, measuring instruments. Now we are going to talk about measuring instruments that we use. So we generally use galvanometer, ammeter, voltmeter. So we will be talking about these 3. First, galvanometer, ammeter and voltmeter. We will not go into their construction, how they are made. We will just see how they are used. Galvanometer is generally used for current detection. Now you may say, sir, current detection or current measurement? You may say measurement also, but specifically we use galvanometer for current detection purpose, because galvanometer shows deflections, okay, deflection in the meter even for currents of order microampere. If you have an ammeter there, ammeter will not be able to detect that. Ammeter is having, let us take a rating from 0 to 1 ampere or 0 to 5 ampere. It may not be able to detect a 3 microampere current, but galvanometer does so. So galvanometer we use generally for current detection or measurement of very small current. Okay. Ammeter is used for current measurement. And voltmeter is used for measuring the potential. Okay. Now when we are measuring the current, we need to connect an ammeter into series, galvanometer into series. So galvanometer and ammeter, they are connected in series in a circuit. Then only they will measure how much current is passing through that. But voltmeter is connected in parallel. Okay. Now voltmeter is connected in parallel to measure the potential, but if you are connecting that, so that may also connecting that voltmeter itself can change the reading, isn't it? Like connecting an ammeter in itself will change the reading of the circuit, because ammeter will also have its resistance, isn't it? Voltmeter will also have some its resistance. So they will change some reading, yes, up to a certain value, but we'll try to make the voltmeter to ideal. Okay, we'll try to keep as ideal as possible. Ideal voltmeter means infinite resistance. Then only zero current will pass through the voltmeter and it will not change the current of the circuit. Ideal voltmeter means infinite resistance. Ideal ammeter means ammeter means zero resistance, then only the current will not change, because ammeter is in the series. So ideal, that should be zero. For galvanometer I am not talking about, because galvanometer we are using generally for current detection. We are using that for current detection. Okay, so just we need deflection there. That is the main concern there. So for ideal ammeter, zero resistance. In real cases, if I talk about galvanometer resistance is of order 10 ohm, 20 ohm, 15 ohm, like that. Real practical cases I am talking about, 50 ohm, like that. Okay. Ammeter 1 ohm, 0.5 ohm, 0.25 ohm, okay, as small as possible. Voltmeter will have very high resistance, okay, 20k ohm, 50k ohm, or like that. As higher as it, okay, better it is. I will say better the measurement it will give us, because it is more ideal. Now converting galvanometer to voltmeter. Now galvanometer will have some range from 0 to few micro, let us take 100 microampere like that, or 250 microampere like that. Okay, we want to measure potential using that galvanometer now. So what we need very high resistance for that, very high resistance. So what we need to do, we need to increase the resistance of the galvanometer. How we can increase the resistance? By connecting a very high resistance in the series. Okay, so galvanometer is there. It is converted to a voltmeter. We will connect a series resistance, and this will behave like a effective voltmeter. Okay, its rating will be, some initial rating will be, some rating of the galvanometer will be there. Okay, let us take galvanometer is having rating of uh, I'm taking a variable. Okay, so let us take that is x microampere. That is the rating of the galvanometer. Okay, full scale means the maximum current that can pass through it is x microampere, and it is having a resistance of g ohm. Now what will be the rating of this voltmeter? So voltmeter will have a rating of how much maximum potential will be there across this now? This total resistance into the total maximum current. So this is G plus Rs into the maximum current is x microampere. Okay, so this much will become my rating of the voltmeter. We'll solve some questions basically using this. So you need to understand that when I'm converting a galvanometer to voltmeter, I need very high resistance. Therefore, we need to connect a resistance in series of the galvanometer such that effective resistance will become very high. Question: galvanometer has a resistance of 50 ohm and it allows maximum current of 5 milliampere. Now this is, you can say, milliampere ranges there of this galvanometer. It can be converted into voltmeter to measure 100 volt by connecting a series in series a resistor of how much? Now let us take, I connected a series resistance of R, and the maximum current here it is given to us as 5 milliampere. Up to 100 volt means the maximum voltage drop that across this will be 100 volts. So I'll say 100 is equals to 5 milliampere, the maximum current, into the total resistance now, that is G plus R. This is how we'll write it. So this will become 5 into 20. So this is 20,000 is equals to G is 50, and this is my series resistance. So from there I got my series resistance, and that need to be 1, this is 950. No, I did a mistake. 20, okay, this should be 20,000. Yeah, 20 into 10 to the power 3, that should be 20,000. So 20,000 minus 50, so this will become 19950. That is option C, 19950. Yeah. Okay, so this is how we can find the equivalent, find the resistance that we need to connect in series. Okay, moving ahead, galvanometer to ammeter. Now ideal ammeter means resistance is very less. So galvanometer is having some resistance of few ohms, 50 ohm, 15 ohm, 20 ohm, like that. So what we need to do, we need to connect a parallel resistance, very small resistance in parallel, such that it is converted to a ammeter, such that the effective resistance will become less. Means what? This is a galvanometer. I'll connect a shunt resistance R shunt in parallel, and this will behave like a effective ammeter. How the range will be increased? It was having, let us take a range of few microampere. Now some current is coming which is very large. So what will happen? This resistance is very small. Most of the current will pass through this. Only very few, very less current, that is of microampere order only, that will pass through the galvanometer, such that the galvanometer full scale deflection is not crossed. Okay, so galvanometer will show its full scale deflection only, but a large current will be able to pass. What happens now? The range is increased. Only galvanometer allows current of few ampere, few milliampere or microampere, but when a shunt resistance is connected in parallel, a large current can pass, and now the range is improved, and the effective range here can be of order of ampere, 0 to 5 ampere, like that. Okay, we got it. And also the resistance of this ammeter is very less, because we are having very small resistance in parallel here. So both the goals are achieved using this. Full scale deflection current of the galvanometer will be given to you. Let us take, this is my Ig. Now here effectively the total current, let us take I, that is coming. Now how I will be divided? In the opposite ratio of the resistances. So if I write Ig is equals to I into opposite ratio of the resistance, Rs divided by G plus Rs. Okay, so sometimes the question can be, the full scale deflection of the galvanometer is this, that is my Ig. It is needed to be converted to an ammeter whose maximum full scale range is this, that will become my I. Okay, the resistance of the galvanometer is this, find the shunt resistance. So use this, you can find the shunt resistance. Let us solve this question here. A galvanometer having coil resistance of 10 ohm shows a full scale deflection for a current of 3 milliampere. So this is galvanometer full scale deflection Ig, 3 milliampere. This is my galvanometer resistance, this is my G. For it to measure a current of 8 ampere, now we are converting it to ammeter whose range is up to 8 ampere. The value of shunt resistance is, so I can say Ig is equals to R shunt divided by R shunt plus galvanometer resistance into my I current. This equation I am using. Okay. Now Ig is 3 into 10 to the power minus 3. This is R shunt divided by R shunt plus, what is galvanometer resistance? This is 10, and into I is 8. Now we need to solve for R shunt. One thing we can see from here is this R shunt will be very less actually. Even if you see the options, they are of order 10 to the power minus 3. So we can neglect that in front of plus 10. Okay, so this we can neglect in front of plus 10. So from there, now simplifying it will become very easy. Okay, so from there it will become 30 divided by 8. 30 divided by 8 into 10 to the power minus 3. So what is 30 divided by 8? This is 3 into 24. Then we are having 60, so 0.85 into 10 to the power minus 3. Not 85, sorry, 75. Yeah. Minus 3 ohm. Getting it? Okay, so in these type of questions, the variations is not there, means these questions are asked. So at least in those questions where there is no variation, those questions should be very clear to you. This variation is there, only one conversion will come. Okay, let us understand it, let us revise it again, and then like it's very probable that these type of questions are asked. In mains, it is very much asked, these converting a galvanometer to ammeter, converting a galvanometer to voltmeter, very much these type of questions are asked. So you can practice that. Another question, as shown in the figure, the voltmeter reads 2 volt across a 50 ohm resistor. The resistance of the voltmeter. Now, here he is saying resistance of voltmeter, but we have understood that voltmeter is having infinite resistance. That is ideal voltmeter. If he is asking such question, it means the voltmeter is having some resistance which is not infinite. This is a real voltmeter. Now we need to find voltmeter. Voltmeter reading is given what? This reads 2 volt. Let us take its resistance is R. So total drop across this resistance is 2 volt. This is 3 volt. How much is dropped across this? 1 volt. Across this drop is 1 volt. Across this the drop is 2 volt. Okay. Now across this drop 1 volt means how much is the current? 1 by 2. Potential divided by resistance. Here the current is 1 by 2. 1 by 2 current is passing through a resistor. How much resistance? 5R divided by R plus 5. I into R, drop is 2 volt, so this is 2. So 5R divided by R plus 5, and this comes out to be 4. So 5R is equal to 4R plus 20, and R comes out to be 20. This voltmeter was having very less resistance. Okay. Let us check our calculations again. This is 3 volt, so this is 1, that is 2. Current become 1 by 2. 1 by 2 into 5R divided by R plus 5, that is my 2. So 2 into 2, 4. Yes, that is 20. Perfect. Another question. When a resistance of 5 ohm is shunted with a moving coil galvanometer, it shows a full scale deflection for a current 250 milliampere. So full scale deflection of 250 milliampere when 5 ohm is shunted with a moving coil galvanometer. Okay, it's the total current. Let us take the galvanometer current is I galvanometer, Ig. So this Ig, if I write, will be equal to total current 250 milliampere, okay, total current into my R shunt is 5 ohm is shunted, so R shunt is 5, so into 5 divided by galvanometer resistance plus 5. Okay. However, when 1050 resistance is connected with it in series, it gives a full scale deflection of 25 volt. Now I'll say 25 volt is equal to 1050 plus my galvanometer resistance G into Ig. So both the equations we need to use here. This is my first equation, this is my second equation. The resistance of galvanometer is, from here we need to solve for G. What we will do? We will divide these two equations. Ig will get cancelled, only variable will be G. Also we need to convert this milliampere to ampere, so you need to multiply here 10 to the power minus 3 for that. Okay, by solving that very easily you can find G from here. Make sure to comment your answer in the comments. What is G in this case? Now we are moving to next topic, that is meter bridge. Basically meter bridge is used to measure unknown resistance. What meter bridge is? It's like this. Here we are having a wire, okay. This wire is having length of 1 meter total. We are having a scale as well, okay. Now this wire is connected with a battery, switch is there, key is there, okay. When we switch it on, current will flow through this wire. Now this wire is a uniform wire. It means the drop across this will be uniform. Potential drop per unit length will be uniform across this wire. Okay. Now we are having one resistance as our known, another resistance unknown, that we need to know. This galvanometer is there, jockey of galvanometer, we are moving on this wire till when we get a 0 reading in the galvanometer, or the 0 deflection in the galvanometer. 0 deflection we got, let us take at a point here. What does it mean now? 0 deflection means this is a balanced Wheatstone bridge. This resistance by this resistance is equal to this resistance by this resistance. So I'll say R divided by this resistance. How much is this resistance? Resistance per unit length will be same, uniform wire is there. Let us take resistance per unit length is lambda, so that will become lambda into L1 is equals to that unknown resistance S divided by this. How much is this resistance? Lambda into this length, so lambda into 100 minus L1. 100 minus L1, why? We are considering L1 in centimeter, okay. So this is my lambda into L1, so this length will become 100 minus L1, lambda will get cancelled. From there I can find my unknown resistance. Just by seeing the values, seeing this length L1 here, I can very easily find the unknown resistance. A question on this. The resistance are connected, resistances are connected in a meter bridge circuit as shown in the figure. The balancing length L1 is 40 centimeter. Okay, this L1 is given to us as 40 centimeter. Now unknown resistance X is connected in series with P. New balancing length is 80 centimeter. The value of X is. First of all, for this condition, if I write 4 by 40 will be equal to that resistance, that is Q, divided by how much the remaining length is 100 minus 40, that is 60. So from here I got Q as 6 ohm. Now case 2, I connected a resistance X in series with P. This is X ohm. Now the new length is that we are getting is 80, that particular case. Then what I will say, P plus X by 80, okay, P is 4, so 4 plus X by 80 is equal to Q divided by 100 minus 80, that is 20. Okay, what is Q? Q is 6. So Q is 6, this is 2 into 4. So 4 plus X divided by 4, this is Q is 6, putting 6 here. So 4 plus 6, 4 plus X, this is 24, X comes out to be 20. So we had connected a 20 ohm resistance in series with P there. Now we are going to talk about potentiometer. In potentiometer we are having two type of configurations, or basically two type of circuits. One is used for measuring unknown EMF, another is used to measure the internal resistance of the cell. Okay, so if a cell is there, it will be having some internal resistance, certainly. Okay, so first circuit will help you to know the EMF of the cell, second circuit will help you to know the unknown resistance of the cell. So first of all, I am talking about unknown EMF. Here we are having two cells. Okay, they are connected. One is, let us take known, another is unknown. First is connected. This is the uniform wire. We are moving this galvanometer key to find the null point. Null point means galvanometer shows zero deflection here. Zero deflection means no current is passing through the galvanometer. When it will happen, the potential across the galvanometer is zero. It means this potential has to be equal to E1 only, then only it is balancing it. Okay. Now in this wire, the potential drop, this is a uniform wire, potential drop per unit length is same. Uniform wire, current is there. Okay, so greater the length, greater will be the potential drop, and that is linear relation. So potential drop across the across this, potential drop per unit length is same. So E1, let us take here the length that balances E1 is L1. So I will say E1 is equals to lambda L1. Getting it? Okay. Now next case. What I did, I connected K2 key here. Now again searching for null point, I got a null point at a length L2. Now here I will say again, null point means zero deflection across galvanometer of the galvanometer. That will happen when the potential across that is same, means zero. This potential has to be equal to this potential. It means here the potential is E2 across this. So E2 is lambda, lambda will remain the same, potential drop per unit length into L2. Okay, initially it was L1. Yeah, I did a mistake. This should be L1. Initially it was lambda into L1. That length I took as L1. Now it is lambda into L2. L1. Lambda into L1. Now it is lambda into L2. Divide these two. So E1 by E2 I got as L1 by L2. Okay. So L1, L2 will be given to you. One known EMF will be given to you. You need to find the unknown EMF. You can use this formula. Quickly you can find it. Next is measurement of unknown internal resistance. Now the cell is there. Its internal resistance is R. I need to find R. Okay. So here what we need to do, you try to understand it properly. We are having one external resistance R here. First case, this key is open, means external resistance is not connected, and now we are finding a null point, and I got a null point here at a length L1. So the total drop across this, the potential across this has to be equal to this potential. What is this potential here? E. So E has to be equal to lambda into L1. Simple. Next case, here you need to understand more clearly. I close the key, current is flowing here in this loop like this. Now I am finding a null point, and my null point is here at a length L2. Now null point here means this potential. How much is this now? E minus IR. That is E minus I into R, where I is the current here, I. This potential is equals to lambda into L2. So E minus IR is equals to lambda into L2. What is I? I is E divided by R plus R into R, or I can say this as E into R divided by R plus R, and this is equal to my lambda into L2. This is second equation, this is my first equation. Now dividing these two equations with each other. Divide these two equations. When you divide, lambda will get cancelled, E will get cancelled. So what it will become? R plus small r divided by R, okay, it will go in the numerator, is equal to L1 by L2. Okay. So 1 plus R by R is equals to L1 by L2. So from here I got R as R into L1 by L2 minus 1. Got the formula for unknown internal resistance. Okay, L1 is greater. Okay, therefore L1 by L2 ratio is greater than 1. It will be a positive internal resistance, positive only. Now let us discuss a question on this. To measure the internal resistance of a battery, potentiometer is used. For R is equals to 10 ohm, the balance point is observed at 500 centimeter. Now we are changing external resistance basically. Now for R is equals to 1 ohm, the balance point is observed at 100 centimeter. The internal resistance is, now here you cannot apply the formula directly. Here my R is changing. Now what was the equation? This equation, E into R by R plus R is equals to lambda into L. Here R is changing in two cases, L is given in those two cases. Okay, then you can write the equation and solve. Let us see. For first case, R is 10 ohm and L is 500 centimeter. Put it. E 10 divided by 10 plus R is equals to 500 centimeter. So 500 into lambda. Second, I'm not converting it to meters because anyways I'll divide, everything will get cancelled, units will get cancelled. Second case, when R is 1, it is 400. Put it. R is 1, so E divided by 1 plus R, and this comes out to be 400 centimeter. Divide these two. These lambda, 400 lambda means 100 lambda will get cancelled there. This E is getting cancelled here. So what it will become? This 5 into 2 it will become here. So this will become 2 into 1 plus R. Okay, 2 into 1 plus R. This is equals to this 10 plus R will go on the other side. 10 plus R will go on the other side. 4 is also there, so 4 will come here into 4. So this is 8 plus 8R is equals to 10 plus R. So from here I can say R comes out to be 2 by 7 ohm. 2 by 7. How much is that? Approximately 0.3. Approximately 0.3 ohm. Yeah. So instead of just remembering the formula, better to understand the concept, because if some variation is there, then you need to tackle that. Okay, now we are coming to RC circuit. This is also you can say one of the important portion, but in advance if we see, RC circuit is more asked. In mains, RC circuit is asked, but not that difficult level. Just you need to understand how to analyze the steady states. Like at steady state, we know the capacitor will behave like an open circuit. Okay, at t is equals to 0, the capacitor will behave like a short circuit. These things you need to understand. Now, first of all, let us discuss about charging. Charging of a capacitor. Okay. So RC, it means there is a capacitor, there is a resistor, a switch is there. Oh, battery, I forgot battery. Here we are having a battery. The switch is closed at t is equals to 0. Now, what will happen? Some charge will come. As a function of time, the charge will increase. We need to find how the charge will change as a function of time, how the current will change as a function of time, how to write that. Let us move in this loop at any instant. Here I am saying the current is charge is plus q, here minus q. Now this is EMF E. Let us move in this loop. So from here plus E, then a drop across the capacitor, so minus q by C, then drop across the resistor. Here the current is I, so minus IR. This is equals to 0. This equation will write, and we know that I is equals to dq by dt. Let's write that I is equals to dq by dt. So E minus q by C is equals to R into dq by dt. I can take R in the denominator, okay, and then I can write this equation this way, you see, divided by E by R minus Q by RC. From here I can integrate it. Time goes from 0 to t, Q goes from 0 to Q, because we know that at t is equals to 0, the charge on the capacitor was 0. I am showing you the derivation, but finally I will tell you how to directly remember that. Those equations of potential as a function of time, charge as a function of time, or current as a function of time, whether charging or discharging, will be very easily be able to write the equations directly. So time, it will become t here, this will become ln E by R minus Q by RC, and limit will go from 0 to Q. Put this as Q, so this is just E by R minus Q by RC, then put it as 0. So if you put Q as 0, so this will become just E by R. Okay, and this is T. Everything is fine, I hope so. Just a minute, yeah. E by R, when I was integrating it, there was differentiation of this part in the denominator as well. So minus 1 by RC, so minus 1 by RC minus 1 by RC, it will come like this. Okay, so from there if I write, it will become E by R minus Q by RC, and this comes out to be E by R into e to the power minus t by RC. Is it right? Yes. So Q by RC is equals to E by R into 1 minus e to the power minus t by RC. So Q comes out to be CE into 1 minus e to the power minus t by tau. T by tau I am saying here. This tau means the time constant, that is my RC. Okay. This tau is RC here, which I say as the time constant. Time constant, and I can say that Q is equals to my Q naught into 1 minus e to the power minus t by tau. What is Q naught? The maximum charge. That is CV. Okay, CV is E here, so CE. So I got charge here as a function of time, and if you try to draw the relation, how it will look like. It is reaching steady state. Q as a function of time, t starting from 0 reaching a steady state. This is my Q naught. Okay, this is how it is going. Now if I try to write the equation for current, I got charge here Q as Q naught into 1 minus e to the power minus t by tau. If I write current, that is dq by dt, just differentiate it. So Q naught into differentiation of 1 as 0, differentiation of e to the power t by tau minus t by tau, it will become minus t by e to the power minus t by tau divided by that differentiation. Okay, into that differentiation, okay, sorry, yeah, into that differentiation, that is minus 1 by tau. Getting it? So minus minus will become plus there, and I is equals to this is Q naught. So this was Q naught by tau into e to the power minus t by tau. So what is Q naught? Q naught was my C into E. Okay, tau was R into C, e to the power minus t by tau. This C got cancelled, so E by R into e to the power minus t by tau, and E by R is I naught, so I naught into e to the power minus t by tau. I naught is my maximum current, peak current. Maximum current will be at t is equals to 0. This is at t is equals to 0. Maximum current is at t is equals to 0. Okay, as time is increasing, the current is decreasing. So if I try to draw the current, how it goes with time. Okay, so the current was initially some value, and then at t is equals to 0, it is getting 0. This is t, this is q, t. And similarly, if I try to write V, potential across the capacitor, so Q I already got, so V is just Q into C. So Vc is equal to Q as Q naught into C into 1 minus e to the power t by tau, e to the power minus t by tau. Okay, so QC is my maximum potential, V naught into 1 minus e to the power minus t by tau. This is the potential across capacitor, that is also decreasing, that is increasing, sorry. At t is equals to 0, the charge was 0, so potential was 0. As t is increasing, the potential is increasing, so potential will also vary like this. Now the important thing you need to understand is, anything which is increasing, that will be of type maximum value into 1 minus e to the power t by tau. Anything which is decreasing will be of type maximum value into e to the power minus t by tau. So if it is increasing, 1 minus e to the power minus t by tau. If it is decreasing, e to the power minus t by tau. Again I am repeating, if it is increasing, 1 minus e to the power minus t by tau. If it is decreasing, just e to the power minus t by tau. Potential is increasing, charge is increasing, current is decreasing. Okay, this was for discharging. Similarly, let us talk about charging. This was for charging. Now I am talking about discharging. Yeah, discharging. The heading was correct there. Yeah, initially it was charging. Now we are talking about discharging. Discharging of capacitor. So discharging of capacitor means initially the capacitor was having some charge, and with the time what is happening, we have closed the switch now, and now what will happen with time, the current, the charge on the capacitor will keep on decreasing. So just you are having a capacitor and a resistor. This charge was some initial value, okay, Q naught, we can say minus Q naught. The switch is closed now at t is equals to 0, okay. This resistances R. Now current will flow like this and the charge will decrease. Let us write the equation in this case. In this case, at any instant I am considering this charge to be Q, this to be minus Q. So when I am moving in the loop, first we are having a gain, I am moving like this, first we are having a gain, that is plus Q by C, then we are having a drop minus IR, and this is equals to 0. This current is coming due to decrease of the charge on the capacitor. So current is negative of the rate of change of the charge. Rate of change of the charge, because charge is decreasing. The current is coming when the charge is decreasing. So if I talk about I, that is minus dq by dt. Let us put it here. Q by C minus, so it will become plus here, dq by dt into R. This is 0. So this will become what? Minus there. So dq, okay, dq, and this is dq by q here I am taking, and this will become a dt minus dt by RC, integrating. Initial charge was Q naught, some charge is Q now, time goes from 0 to t, RC is constant, so minus t by RC, and this is ln of Q by Q naught. So basically Q is equals to Q naught into e to the power minus t by RC, which is tau. This is how my charge is. Here charge is decreasing. Anything which is decreasing is of type e to the power minus t by tau. So Q naught into e to the power minus t by tau. Simple. Tau is RC. Okay. If I write current here, minus dq by dt minus differentiated, Q naught is constant, e to the power minus t by RC into minus 1 by RC. Okay. So what it is now? Here it will become Q naught by RC into e to the power minus t by RC. So this is again I naught, the maximum current, into t to the power minus t by RC. The maximum current is at t is equals to 0. Okay. Current is decreasing. Yes, current is decreasing. So e to the power minus t by RC. Potential, if you write Q into V is equals to, Q is equals to CV. Did I mistake? I did any mistake previously? Okay, charge I mentioned there previously, just seeing I did any mistake. Q is equals to, okay, I did a mistake here. V is equals to Q by C. Yeah, here is a mistake. V is equals to Q by C, not into C. V is equals to Q by C. Okay, so Q naught by C. Yeah, and that is my V naught. Corrected that. So similarly here V, if I write, that is my Q by C, What is Q? Q is equals to Q naught e to the power minus t by tau by C. So Q by C, this is my V naught e to the power minus t by tau. This is decreasing with time. So all the three quantities are decreasing with time like this. So any of that I can plot it for you. Let us plot Q. So Q with time, it will go like this. This is my Q naught. Now the important thing. For charging, if I talk about, first of all I am coming to charging. Okay. Charging of the capacitor. At t is equals to infinity, the current at t is equals to infinity will become 0. The capacitor will behave like a open circuit at t is equals to infinity. Okay. So at t is equals to infinity here, in case of charging, at t is equals to infinity, capacitor behaves as open circuit, and at t is equals to 0, current is maximum, it behaves like a short circuit. Short circuit means potential is 0. If you put t is equals to 0 here, the potential will become 0. So capacitor behaves as my short circuit. This you should remember. Okay, everything is clear. Now we are moving to questions part. Let us see what type of questions are asked from RC circuit in mains. In mains, very simple, just steady state type of things, or just formula, or I'll say fundamental based type of questions are asked. So some varieties we have considered here. Let us see. A galvanometer of 2 ohm resistance is connected in the given circuit. The ratio of charge stored in C1 and C2 is ratio of charge stored in C1, and this is my C2. Now here he is saying it means this circuit is at steady state. Circuit is at steady state means the capacitor behaves like a open circuit. The current will, how the current will move? It will move like this, I from here, then from the galvanometer, then from here. So current is going like this. What is the potential across capacitor C1? What is the potential across capacitor C1? That is I into galvanometer resistance plus 4 ohm. How much is galvanometer resistance? 2. So I into 4 plus 2, 6I. This is V1. What is V2 across this C2? I into 6 plus G. I into 6 plus G, 2. Okay. So V2 is 8I. I have to find the ratio of charge. Q is equals to C into V. Q is equals to C into V. So when I say Q1 by Q2, that is C1 V1 by C2 V2. What is C1? 4. What is V1? 6I. What is C2? 6. What is V2? 8I. I got cancelled, 6 got cancelled. This becomes 2. This is 1 by 2. This becomes 1 by 2. D option. Everything is fine? Yeah. C1 by C2, that is my 4 by 6. V1 by V2 is 6 by 8. Okay, that comes out to be 1 by 2. Perfect. So at steady state, capacitor behaves like an open circuit. Further, in the network shown below, the charge accumulated in the capacitor in steady state will be similar type of question. At steady state, here current will be 0. Okay, so here the current is 0. The current will be flowing like this. It will go like this, I, here I, here I, okay, here it is 0. So in this loop, if I see how much is the current, like in this loop, if I write the Kirchhoff law, so I'll say that 3 is equals to 4i plus 6i. 3 is equals to 4i plus 6i. So 3 is equals to 10i, comes out to be 10i. I comes out to be 3 by 10. I is 3 by 10. How much is the potential across this 6 ohm? So that will be 6 into I. So potential V, this is across 6 ohm I am writing, okay. How much is that? I into 6. 1.8. That is 1.8. That potential is across this only. The potential across 6 ohm is the potential across this. That is 1.8 volt. The current through this 6 ohm resistance is 0. Potential across this is 0. It means this same potential is across the 4 microfarad capacitor. Q is equals to CV. 4 into 1.8 microcoulomb. 7.2 microcoulomb. 7 point, I did a mistake. Yeah, I did a mistake. What is that? Let us see. What is that mistake? This is 3 volt. This is 4 ohm. This is 6 ohm. The current becomes here how much? That is 3 divided by 10. 6 plus 4, 10. 3 by 10. Yeah. Yes. So the potential across this will become 3 by 10 into 6. That is 1.8. Q, that is C into V. So C is 4 into 1.8. Okay. So this will become 7.2 microfarad. Okay, there may be some mistake. Let us write this as 7.2, not farad, microcoulomb. Yeah, 7.2 microcoulomb. There might be some typing mistake here. Getting it? So what we did, capacitor at steady state behaves like open circuit. Found the potential drop across the capacitor. How much that we got that? We got that as 3 by 10 into 6, that is 1.8. That potential will be across this capacitor and this resistance. But this resistance is having 0 current. So no drop across this. So that is the drop across the 4 microfarad capacitor. So that drop Q, so V we got, C is 4, okay. So Q we need to find, that Q is equals to CV, we got 7.2 microcoulomb. Getting it? Okay, another question we are having here, let us read it out. The electric field between two parallel plates of capacitor is this, of two parallel plate of 1.5 capacitor drops to 1/3 of its initial value in 6.6 microsecond, okay. When the plates are connected by a thin wire, the resistance of this thin wire is. So plates are connected by a thin wire, you can consider this a condition like this also, okay, having a resistance like this is my capacitor. Now here is saying that the electric field drops to 1/3. Electric field drops to 1/3 means potential drops to 1/3, isn't it? So potential drops to 1/3. How to write the potential across a capacitor discharging? V is equals to V naught into e to the power minus t by tau. This formula you already know. What is V now? V is V naught by 3 is equals to V naught into e to the power minus t by tau. So 3 is equals to e to the power t by tau. From there, t is equals to tau is RC ln 3. Put the values. What is R? R we need to find. What is T? T is 6.6 microsecond. 6.6 micro. R. What is C? C is 1.5 micro farad. And what is ln3? That is 1.1. Okay. So 1.1 into 6. 10 to the power minus 6 got cancelled. Yeah. So R comes out to be 6 divided by 1.5, and that is 4 ohm. So this comes out to be 4. Okay. So till here we have seen all the varieties, almost all the varieties of the questions that are asked in mains. Each concept we have taken into detail, discussing the concepts, solving the questions, and at the same time I hope you are also solving many of the answers I asked from you. So you might have solved those questions and might have mentioned few things in the comment section. So whatever doubts and queries if you have, let us take you have some conceptual doubt in between, so you must mention in the comments. Also share your feedback in the comment. We'll meet in the next video. Thank you all.